On a screen in a quiet observatory, the oldest light we can see does not look like light at all. It looks like a mottled oval, a full sky map covered in small differences of temperature, each one only a tiny fraction of a degree from the next. The colors are artificial. The pattern is real. It is the cosmic microwave background, the afterglow from a time when the universe was still young enough that atoms had only just begun to exist. And when scientists study that map, they are not looking at stars or galaxies. They are looking at a wall of ancient radiation, the farthest surface ordinary light can carry back to us. Behind that wall is the question this video follows. What was before the Big Bang, and why does science still have no final answer? The light in that map was released about 380,000 years after the hot early universe began expanding and cooling. That sounds close to the beginning until you compare it with the age of the universe itself, which is about 13.8 billion years. In human terms, 380,000 years is an enormous span of time. In cosmic terms, it is the first breath after a very long night of physics that no telescope can photograph directly. Before that moment, space was filled with hot plasma. Photons could not travel freely. They scattered again and again from charged particles, as if every direction were fogged with light. The strange thing is that this oldest visible light already contains structure. It is almost uniform, but not perfectly uniform. Some regions were slightly denser than others, some were slightly warmer or cooler. Those tiny differences became the seeds of galaxies, clusters, filaments, and voids. The Milky Way, the spiral arms, the dust lanes, the star-forming clouds, the worlds orbiting distant suns, all trace back in some way to these early variations. They are not dramatic in the map. They are faint. They are measured in microkelvin. But over billions of years, gravity turned those small differences into the cosmic web. To ask what came before the Big Bang is not the same as asking what lies beyond a distant galaxy or what is hidden behind a dark nebula. Those are hard questions, but they still belong to space. A telescope can point toward them. A detector can gather more photons. A spacecraft can travel outward and send telemetry home. The beginning of the universe is different because the question pushes into a region where the usual meanings of distance, time, and cause become unstable. The word before depends on time already existing, and one of the deepest uncertainties is whether time, as physics describes it, can be extended beyond the hot early state. Scientists do not say that nothing is known. That would be wrong. The Big Bang model is not a guess built from imagination. It is supported by expanding galaxies, the cosmic microwave background, the abundance of light elements, and the large-scale pattern of structure across space. But the model does not open every door. It describes a universe that was once hotter, denser, smoother, and smaller in scale than it is today. It does not automatically tell us whether that hot, dense state was the absolute beginning, the result of an earlier phase, or the edge of a theory that has not yet been completed. If the oldest questions in space are what bring you here, subscribing keeps the next long journey close to the same dark horizon. The word Big Bang can be misleading. It sounds like an explosion in empty space, as if matter burst outward from a central point into a waiting void. That is not what the evidence indicates. The galaxies are not flying away from a place where the universe began. Space itself is expanding, carrying distant galaxies away from one another. No matter where an observer is placed, if that observer sees far enough, the pattern looks broadly similar. Distant galaxies recede. Their light is stretched. The farther they are, on average, the more redshifted they become. Redshift is one of the first concrete clues. When light from a galaxy is spread into a spectrum, certain dark or bright lines appear at wavelengths determined by atoms and molecules. If those lines are shifted toward longer wavelengths, toward the red and infrared, the galaxy is moving away through expanding space. Edwin Hubble and others helped establish this pattern in the early 20th century, but the idea of an expanding universe also came through equations, through general relativity, and through the work of scientists who realized that space itself did not need to remain static. The sky was not simply filled with islands of stars, it was changing on the largest scale. Run the expansion backward in mathematics, and the universe becomes denser. Galaxies draw closer together, the spaces between clusters shrink, gas grows hotter. The radiation that now arrives as cold microwave background light becomes visible, then ultraviolet, then X-ray, then gamma radiation. Matter stops being arranged as galaxies and stars. At earlier times, atoms cannot hold together. Earlier still, nuclei cannot remain stable. The universe becomes a hot, compressed sea of particles and radiation, not because everything is moving into a single point in ordinary space, but because the scale of space itself is being wound backward. That backward calculation is powerful, but it is not unlimited. Equations can be trusted only inside the domains where the underlying theory still works. General relativity describes gravity on cosmic scales with extraordinary success. Quantum theory describes particles and fields with equal success at very small scales. Near the earliest moments, both are needed at once. The universe becomes so dense, so energetic, and so small in scale that gravity and quantum physics can no longer be treated separately. The problem is not a lack of imagination. It is that the best-tested theories do not yet merge cleanly there. This is why the phrase "before the Big Bang" sits at the edge of science rather than outside it. It points to a real gap in understanding. It asks whether the hot expanding state had a cause. It asks whether there was an earlier universe, a previous contraction, a quantum beginning, an inflationary field, or a deeper condition where time had a different meaning. Researchers have proposed many possibilities. Some are mathematically sophisticated, some make predictions that might one day be tested, some remain difficult to separate from speculation. None has yet become the settled story of cosmic origins. The evidence begins not at the beginning itself, but with traces that survived. A telescope does not observe the first instant. It observes consequences. A radio receiver hears the leftover microwave glow. A spectrograph measures redshift. A satellite maps small temperature differences. A galaxy survey records where hundreds of millions of galaxies sit in space. A supercomputer follows dark matter particles through expanding grids and compares the result with the structure we see. Each tool touches a different part of the same ancient event, but none reaches all the way through it. The cosmic microwave background is often called the oldest light in the universe, but even that phrase needs care. It is the oldest light that could travel freely to us. Before it was released, light existed, but it was trapped in constant interaction with charged particles. The universe was opaque, not dark. A human eye placed inside that plasma would not have seen stars or blackness. It would have been surrounded by light from every direction, too dense and too hot for anything like ordinary vision. Then, as the universe expanded and cooled, electrons joined atomic nuclei, mostly forming hydrogen and helium. The fog cleared. Imagine a camera that cannot look through a cloud, but can still photograph the outer surface of that cloud. The cosmic microwave background is a little like that. It is not the Big Bang itself. It is the surface from which the universe became transparent. The pattern on that surface carries information from earlier times, because sound waves and density variations moved through the plasma before the light was released. Those patterns are preserved as tiny differences in temperature and polarization. They are a fossil record written not in stone, but in radiation. The comparison with fossils is useful only up to a point. A fossil bone comes from one animal in one place. The cosmic microwave background is all around us. Every direction in the sky contains it. Radio telescopes, microwave detectors, balloon experiments, and space missions have measured it more and more precisely. COBE detected its near-perfect blackbody spectrum and large-scale fluctuations. MAP refined the map. Planck measured the microwave sky with still greater detail. Each mission improved the same basic picture, a universe that began hot, dense, expanding, and remarkably close to uniform. Remarkably close does not mean perfectly smooth. If it had been perfectly smooth, gravity would have had no preferred places to work. No denser regions would have attracted more matter. No clusters would have grown. No galaxies would have formed. The slight unevenness of the early universe is essential. It gave gravity something to amplify. Over time, dark matter collected into halos. Gas fell into those halos. The first stars ignited. Galaxies assembled, merged, spun, collided, and formed the structures that telescopes now record in deep images and redshift surveys. A long exposure from a space telescope can show galaxies whose light has traveled for more than 13 billion years. Some appear as red smudges, stretched by expansion into infrared wavelengths. They are not close to the Big Bang in an everyday sense. Hundreds of millions of years had already passed. Stars had formed. Heavy elements had begun to appear. Black holes may already have been growing in the centers of young galaxies, but compared with the age of the universe, these galaxies belong to cosmic dawn. They show how quickly structure emerged after the early smoothness began to break into islands of light. This matters because the question before the Big Bang cannot be separated from the question after it. A good theory of the beginning must not only sound possible, it must produce a universe like the one we observe. It must explain why space is so uniform on large scales, why it appears geometrically close to flat, why the temperature pattern of the microwave background has the shape it has, why galaxies formed in the distribution they did, and why the light elements exist in their observed amounts. A proposal about before must survive the evidence from after. One of the earliest tests comes from the first few minutes. Long before atoms formed, when the universe was still extremely hot, protons and neutrons combined into the first light nuclei. This process is called Big Bang nucleosynthesis. It produced mostly hydrogen and helium, with small amounts of deuterium, helium-3, and lithium. The predicted abundances are not arbitrary. They depend on temperature, density, expansion rate, and nuclear reactions. When astronomers compare those predictions with observations, especially for helium and deuterium, they find strong support for a hot early universe. Nucleosynthesis does not tell us what happened at the first instant. It begins after the universe had already cooled enough for nuclear reactions to proceed in a stable way. Still, it acts like a checkpoint. Any earlier theory must pass through it and arrive at the same light element pattern. A bounce model, an inflationary model, a quantum beginning, or any other scenario cannot simply replace the Big Bang and ignore what follows. It must lead into the hot, radiation-dominated conditions that produced those nuclei. The universe may have had a deeper origin, but it still had to become the universe whose chemistry we can measure. Earlier than nucleosynthesis, the universe becomes less familiar. There are no atoms, no stars, no nuclei, no chemistry. Temperature is so high that matter exists as particle fields, radiation, quarks, gluons, leptons, and other components of the Standard Model. Some stages are supported by particle physics. Others are inferred with increasing uncertainty as energies exceed what experiments can reproduce directly. A particle accelerator on Earth can imitate some conditions of the early universe for tiny fractions of a second in tiny volumes. It cannot rebuild the whole cosmic beginning. The further back the calculation goes, the more the universe stops resembling a place and starts resembling a condition. There are no coordinates that would make sense to a spacecraft, no direction toward the origin, no outside view. Space is not a container holding the event. Space is part of the event. That is one reason the question feels so difficult. Our language evolved for objects moving through time and space. The early universe asks us to use those same words for a state where time and space themselves may have been emerging, changing, or losing their ordinary meaning. The standard cosmological model works extremely well from a tiny fraction of a second after the beginning onward, depending on how one defines the boundary of known physics. But the very earliest phase remains uncertain. One of the most important ideas about that phase is cosmic inflation. Inflation proposes that the universe underwent a very brief period of extremely rapid expansion, stretching space by an enormous factor. It was not an explosion faster than light through space. It was the expansion of space itself. That distinction matters because relativity limits motion through space, not the rate at which space can expand. Inflation was introduced to solve several puzzles. The cosmic microwave background looks almost the same in opposite directions of the sky, even though those regions would not have had enough time to exchange light signals in a simple non-inflationary model. The universe also appears very close to flat on large scales, a condition that would otherwise require extreme fine-tuning. Inflation can smooth and flatten space by stretching it, while also magnifying tiny quantum fluctuations into the seeds of cosmic structure. It is a powerful idea, but the mechanism behind it remains unsettled. The inflationary period, if it occurred, would have ended by releasing energy into particles and radiation, reheating the universe and setting up the hot Big Bang phase. In that picture, the Big Bang is not necessarily the absolute beginning. It is the hot expanding state after inflation. Then, the question becomes sharper. What was before inflation? What was the inflating field? Why did inflation begin? Did it begin everywhere, or only in a region that became our observable universe? Did it have its own beginning, or does it extend into a larger structure beyond what we can see? Some versions of inflation lead to an idea called eternal inflation. In these models, inflation ends in some regions, but continues in others. Pocket universes could form like regions where the field decays into hot expanding space, while the larger inflating background keeps producing more regions. This is one route to multiverse thinking. It is not a single confirmed theory. It is a consequence of certain mathematical models. The difficulty is evidence. If other regions exist beyond our observable horizon, light from them may never reach us. A theory that cannot be tested directly becomes hard to distinguish from a mathematical possibility. This does not make the idea meaningless. Science often begins with theories whose predictions are indirect. Dark matter was inferred from gravity before anyone knew what particle, if any, might compose it. Black holes were solutions in equations before they were observed through X-rays, stellar motion, gravitational waves, and radio interferometry. But the standard is still evidence. A multiverse connected to inflation would need observable traces, statistical patterns in the cosmic microwave background, gravitational wave backgrounds, curvature, or some other measurable signal. Without that, it remains an open possibility rather than a solved origin. Another reason inflation is still under investigation is the search for primordial gravitational waves. Inflation may have produced ripples in spacetime itself, and those ripples could leave a faint twisting pattern in the polarization of the cosmic microwave background. This pattern is called B-mode polarization. Detecting it would not answer every question, but it would reveal something about the energy scale of inflation and the physics of the earliest universe. Claims have come and gone. Dust in our own galaxy can imitate the signal. Instruments must separate the faint cosmic pattern from foreground contamination with extreme care. That is the character of cosmology near the beginning. The signal is faint, and the foregrounds are close. A detector on a mountain or in space measures microwave photons that have crossed almost the entire observable universe, but those photons pass through the Milky Way before reaching us. Galactic dust emits polarized light. Synchrotron radiation adds noise. Instrument calibration matters. Beam shape matters. Statistical assumptions matter. A possible clue from the first fraction of a second can be hidden behind particles of dust drifting between stars a few hundred light-years away. The search continues because the reward is enormous. A gravitational wave imprint from inflation would be a message from a time earlier than the cosmic microwave background, earlier than atoms, earlier than nuclei, earlier than any light that can travel freely. It would not show us a picture. It would show us a pattern, a correlation, a trace in polarization. Modern cosmology often advances this way, not through a dramatic image of the beginning, but through a tiny statistical excess in data that has to be checked, rechecked, and compared against every known source of error. While inflation points one way, other models point in another. Some researchers have asked whether the Big Bang was not a beginning, but a bounce. In a bounce model, the universe may have gone through a previous phase of contraction. Space could have been shrinking before it began expanding. At high density, instead of collapsing into an infinite singularity, new physics might have caused the contraction to stop and reverse. Our expanding universe would then be the aftermath of that reversal. It is a striking idea, but it depends on physics that is not yet fully established. The appeal of a bounce is easy to understand. General relativity, when run backward without quantum corrections, tends toward a singularity, a place where density and curvature become infinite and the theory stops giving sensible answers. Many physicists suspect that infinities in a theory are not physical objects, but signs that the theory is being pushed beyond its range. In that sense, a bounce replaces the mathematical breakdown with a transition. The universe becomes extremely dense, perhaps quantum gravitational, and then expands. The question before the Big Bang becomes a question about what the previous phase was like. Several bounce ideas exist. Loop quantum cosmology, inspired by loop quantum gravity, suggests that quantum properties of spacetime could create a repulsive effect at extreme density. Ekpyrotic and cyclic models imagine a slow contraction smoothing the universe before a bounce, sometimes connected to ideas from higher dimensional physics. Other models use modified gravity or special forms of matter and energy. They differ in details, but they share one goal: to avoid an absolute beginning by extending cosmic history through a transition. The challenge is to make the transition stable, predictive, and consistent with everything we observe. A previous universe, if it existed, would not necessarily resemble ours. It might have been colder and emptier before contraction, or filled with structures that were crushed and transformed beyond recognition. It might have had galaxies that no trace can survive from, or no galaxies at all. The bounce itself would erase or reshape most direct evidence. That makes the model difficult to test. Scientists look for indirect remnants, patterns in the microwave background, deviations from inflationary predictions, special gravitational wave spectra, or non-Gaussian signatures in the distribution of primordial fluctuations. Non-Gaussianity is a technical word, but the basic idea is simple. Random fluctuations can have different statistical shapes. Inflation usually predicts a particular kind of near-Gaussian pattern, depending on the model. Some alternatives predict stronger departures from that pattern. If the temperature variations in the cosmic microwave background or the distribution of galaxies show certain kinds of correlations, they could support one early universe scenario over another. The difficulty is that the observed universe gives us only one sky. Cosmologists cannot rerun the beginning many times. They must extract statistics from the single cosmic history available. This single history is vast, but it is still one sample. The observable universe contains hundreds of billions of galaxies, perhaps more, each with stars, dust, gas, black holes, planets, and dark matter halos. Yet all of it belongs to one region of spacetime, visible from one cosmic position. Beyond the horizon, there may be more universe. We cannot see it because light from there has not had enough time to reach us since the hot early state. The universe may be far larger than the part we observe. It may even be infinite. But science has to begin with the region whose signals arrive. The observable horizon is not a wall in space. It is a limit set by time, expansion, and the speed of light. The cosmic microwave background reaching Earth today was emitted from matter that is now about 46 billion light-years away, because space expanded while the light traveled. That does not mean the universe is 46 billion years old. It means distance in an expanding universe is not measured the same way as distance across a static room. The geometry of spacetime matters. Cosmology is a science of moving scales as much as moving objects. At the edge of these scales, the word before becomes even more unstable. In ordinary life, before means earlier on a clock, before sunrise, before a collision, before a signal arrives. But if time itself is part of the universe's structure, and if that structure emerged from an early quantum state, asking what happened before time may be like asking what is north of the North Pole. The question may not have a standard answer. That possibility is not a dismissal. It is a warning that language may be carrying us beyond the map. Some approaches lean into this idea. The Hartle-Hawking no-boundary proposal, for example, suggests that the universe may not have a sharp beginning in time in the ordinary sense. Near the beginning, time could behave more like a spatial dimension, removing the edge where a singularity would otherwise appear. In that picture, the universe has a finite history, but no boundary like a first moment that requires a previous moment. It is difficult to visualize because it asks us to stop treating time as a simple line extending backward forever. No-boundary ideas are not settled cosmology. They belong to the effort to combine quantum theory with gravity and to describe the universe as a whole. They show how strange the problem becomes when scientists take the equations seriously. A beginning might be a boundary. It might be a bounce. It might be a transition. It might be a place where ordinary time is not the correct variable. Each option is an attempt to avoid the same difficulty, a classical singularity where known physics stops. The singularity itself is often misunderstood. When popular language says the universe began as a point, it can suggest a tiny object sitting in darkness. In the simplest general relativistic models, the singularity is not a point inside space. It is a limit where the scale factor of the universe goes to zero and density becomes infinite. For an infinite universe, every region would have been compressed, not gathered at one central location. For a finite universe, the geometry is still not the same as a ball exploding into emptiness. The mathematics is subtler than the image. Most physicists do not treat the singularity as a physical description of what really happened. They treat it as a sign that classical general relativity has been extrapolated too far. The same theory that predicts the singularity also tells us that curvature becomes extreme, and extreme curvature is exactly where quantum effects of spacetime may matter. Without a confirmed theory of quantum gravity, the first instant remains unresolved. It is not that scientists have ignored the question. It is that the question sits where the two most successful frameworks in physics have not yet been fully joined. Quantum gravity is not one theory. It is a family of attempts. String theory, loop quantum gravity, causal dynamical triangulations, asymptotic safety, emergent spacetime ideas, and other approaches all try to understand how gravity behaves at the smallest scales. Some are more developed than others. Some connect to particle physics. Some focus on the structure of spacetime itself. Cosmology offers one of the few possible laboratories for these ideas, because the early universe may have reached energies where quantum gravity mattered. But the laboratory is 13.8 billion years away in time, and it cannot be rebuilt. The Planck time is often named in this context. It is about 1043 seconds after the extrapolated beginning, an interval so small that ordinary intuition has no grip on it. Earlier than this, current physics cannot confidently describe the universe. The Planck length, Planck energy, and Planck density are not magic thresholds where everything is known to change in a specific way. They are scales where quantum gravitational effects are expected to become important. They mark the edge of reliable extrapolation, not a completed theory. A clock cannot be placed at the Planck time. No spacecraft could send data from there. No atom existed to vibrate. No observer could stand outside and watch. The only access comes through mathematics and through later traces. That is why the beginning is not like the surface of Mars, where a rover can photograph stones and drill into rock. It is more like trying to infer the first vibration of a bell from a sound that has echoed, scattered, cooled, stretched, and mixed with noise for almost 14 billion years. Still, The later traces are rich. The power spectrum of the cosmic microwave background shows how temperature fluctuations vary with angular scale. Peaks in that spectrum reveal sound waves in the early plasma. The first peak indicates the geometry of space is close to flat. Other peaks constrain the amounts of ordinary matter, dark matter, and radiation. Polarization adds more information. Large-scale structure surveys provide an independent record of how matter clustered later. The universe may be old, but it has left a detailed statistical archive. The archive extends through galaxies. A redshift survey does not simply produce a catalog. It reveals a cosmic web, with galaxies tracing filaments and clusters around enormous voids. Dark matter forms the invisible scaffolding. Ordinary matter glows where stars ignite and gas is heated. On the largest scales, this structure still carries the imprint of early acoustic waves, known as baryon acoustic oscillations. They form a kind of standard ruler, a preferred separation scale left over from the early plasma. The pattern helps measure cosmic expansion and test the same model that reaches back toward the beginning. Dark matter and dark energy complicate the story because they are essential to the model and still not fully understood. Dark matter is inferred from gravitational effects, galaxy rotation, cluster dynamics, lensing, and the growth of structure. Dark energy is the name given to the observed acceleration of cosmic expansion. Neither should be treated as a solved substance with a simple explanation. Yet the standard cosmological model, with ordinary matter, dark energy, radiation, and initial fluctuations, matches a remarkable range of observations. Any deeper origin story must connect to that success. This is one reason the before question can never be answered by saying anything one likes. A previous universe has to produce the right microwave background. A quantum beginning has to produce the right fluctuation spectrum. A multiverse model has to explain why our region has the observed constants without losing predictive power. A cyclic model has to pass through bounces without accumulating contradictions. A no-boundary model has to connect abstract mathematics to measurable quantities. The unknown is wide, but it is not empty. It is fenced by data. In 1964, two radio astronomers were trying to understand a persistent noise in their antenna. It did not go away when they checked the equipment. It did not match an obvious local source. It seemed to come from every direction. That noise became one of the most important discoveries in modern cosmology, the cosmic microwave background. The signal had been predicted before it was found, and its discovery helped transform the Big Bang model from one possibility among others into the dominant framework for understanding cosmic history. The instrument was not looking for a philosophical answer. It was dealing with radio noise, horn antennas, calibration, and unexplained excess temperature. This is often how the universe becomes known, not through direct access to the most dramatic event, but through stubborn details. A line in a spectrum shifted from where it should be. A star wobbling under the pull of an unseen planet. A galaxy rotating too quickly for its visible mass. A detector registering a strain smaller than the width of a proton. The extraordinary enters through measurement. The cosmic microwave background is now measured as a black-body radiation field with a temperature of about 2.7 Kelvin. It is cold now because space expanded. Radiation stretches with space, shifting to longer wavelengths and lower energy. At the time it was released, it would have corresponded to a temperature of roughly 3,000 Kelvin, hot enough to glow. Earlier, it was hotter still. The same light that now whispers in microwave detectors once filled the young universe as visible and infrared radiation, part of a bright plasma that no eye could have crossed. Every cubic centimeter of space today contains hundreds of microwave background photons. They pass through planets, stars, bodies, detectors, and empty intergalactic regions. They are ancient, but not rare. They are everywhere. Most of the photons in the universe belong to this background, not to starlight. This means the night sky is not truly empty between the stars. It is filled with the cooled remains of the early hot universe, stretched until human eyes cannot see them, waiting for instruments built to the proper wavelength. The CMB tells us the universe was hot and dense, but it does not by itself prove what came before that condition. It is a boundary of visibility and a carrier of earlier physics. Some features may point toward inflation. Some anomalies have been discussed, such as unusual alignments, cold spots, or low power at large angular scales. Scientists study them carefully, but most are not accepted as decisive evidence for new cosmology. In a single sky, chance patterns can look meaningful. A cautious science must separate genuine signals from statistical accidents and from the ways humans choose what to notice. This caution can feel unsatisfying because the question is so large. People want a clean answer. A beginning, a cause, a previous world, a nothing that became something. But the universe does not owe us a story shaped like human expectation. It gives measurements. It gives background radiation, redshifts, abundances, lensing maps, galaxy catalogs, and mathematical constraints. The story has to be built from those pieces, and when the pieces stop, honesty requires the narration to slow down. Nothing is a particularly dangerous word here. In everyday language, nothing means an empty box, a dark room, a blank space with no objects inside. In cosmology, that is not nothing. Empty space can have fields, quantum fluctuations, vacuum energy, curvature, and laws. A vacuum is not the absence of physics. It is a physical state. When someone says the universe may have come from nothing, the word usually carries technical meaning that is very different from ordinary emptiness. Confusion begins when the technical and everyday meanings are treated as the same. Quantum field theory describes fields permeating space. Particles are excitations of those fields. Even what we call a vacuum can have structure. It can produce measurable effects such as the Casimir effect in certain laboratory conditions. But a quantum vacuum exists within a framework of space-time and laws. Asking where that framework came from is a deeper question. A theory in which space-time itself emerges from a quantum state is not simply a particle appearing in an empty room. It is a proposal about the origin of the room, the clock, and the rules together. Some cosmologists and philosophers of physics therefore distinguish between a beginning from a prior physical state and a beginning without a prior classical spacetime. In the first case, before may be meaningful. There may be a contracting universe, a pre-inflationary phase, or a larger inflating background. In the second case, before may not apply. Time may be emergent, approximate, or only defined after a certain condition. The difficulty is that both kinds of ideas can be expressed mathematically, but the universe must decide through evidence which, if any, matches reality. Evidence for pre-Big Bang physics is hard because extreme expansion can erase traces. If inflation lasted long enough, it would stretch away many signs of what came before. Any curvature, relic particles, or irregularities from an earlier phase could be diluted beyond observation. That makes inflation both powerful and frustrating. It explains why the universe looks smooth, but by smoothing it, it may also hide its own starting conditions. The earliest history could be concealed by the very process that made later cosmic history possible. Picture a rough surface stretched until every bump becomes nearly flat across the part you can see. From inside that stretched region, the original roughness is gone from view. Inflation does something like this to space, if the model is correct. It can take a tiny region and expand it until it becomes larger than the observable universe. What was outside that region, or what came before the expansion, may no longer leave accessible marks. The universe we see could be a smoothed patch of a much larger and stranger whole. This does not mean inflation is untestable. It makes predictions about the spectrum of fluctuations, the flatness of space, and possible gravitational wave signatures. Observations have supported some broad inflationary expectations, especially the near-scale invariant pattern of primordial fluctuations. But many inflationary models can fit current data, and the details of the inflated field remain unknown. Inflation is less a single completed theory than a framework with many versions. Some may be ruled out, others may survive. The exact mechanism remains an open target. The word mechanism is important. To say the universe inflated is not the same as knowing what caused inflation. Physicists often model it with a scalar field, a field with a value at every point in space. The field's energy can drive rapid expansion, and when the field changes state, that energy can become particles and radiation. But the identity of the field is unknown. It has not been detected in a laboratory. Its potential energy curve is not measured the way a planet's orbit is measured. It is inferred from what the early universe may have required. If inflation had a beginning, then it does not answer the ultimate before question. It moves the question one step back. What set up the inflating field? Why did it have the right properties? Was there a lower entropy condition before it? Did quantum fluctuations start it? Was it eternal into the past, or must even eternal inflation have a boundary? There are theorems suggesting that many inflationary spacetimes cannot be extended infinitely into the past, but the interpretation depends on assumptions. The edge remains contested. The issue of entropy appears repeatedly in origin questions. Entropy is often described as disorder, though that is only a rough shorthand. It is more precise to think of it as the number of microscopic arrangements compatible with a macroscopic state. The early universe was hot and dense, which sounds high entropy, but gravitationally it was very special. Matter was distributed with extraordinary smoothness. Because gravity tends to clump matter, a smooth early universe may represent a low entropy condition in the gravitational sense. Explaining that special condition is one of the deepest problems. Inflation can help by stretching and smoothing a region, but some critics argue that inflation itself may require special initial conditions. Others argue that quantum cosmology or eternal inflation can address this. Bounce and cyclic models often try to explain the low entropy beginning through a previous smoothing phase, such as slow contraction. No consensus exists. The arrow of time, the reason the past is different from the future, runs through the entire question. A universe before the Big Bang would still need to explain why time has the direction we experience. The arrow of time is visible in ordinary things. A shattered glass does not reassemble. Heat flows from hot to cold. Stars burn fuel and leave remnants. Galaxies merge more easily than they unmerge. Black holes grow by swallowing matter and merging with other black holes. These processes point toward increasing entropy. If the universe had a previous phase, did entropy continue through the bounce? Did it reset? Did it grow from cycle to cycle? A cyclic universe sounds simple until entropy is included. Then each cycle must avoid becoming messier beyond recovery. Some cyclic models address this by making each cycle larger or by diluting entropy through expansion. Others use conformal transformations, changing the way the far future of one cosmic era relates to the beginning of another. These ideas can be elegant, but elegance is not evidence. Scientists look for consequences, unusual patterns in the microwave background, specific gravitational wave backgrounds, or other measurable differences from standard inflation. Without such traces, the models remain possibilities on the shelf of theory, not final answers. A blackboard can hold many universes. Equations can describe bounces, branes, quantum tunnels, no boundary states, and inflating landscapes. The real universe is less generous. It happened once, at least from our point of view, and it left whatever evidence it left. Every proposal must eventually face the sky. A CMB map, a polarization spectrum, a catalog of galaxies, a measurement of curvature, a limit on primordial gravitational waves, a helium abundance in an old gas cloud. These are not decorations added to a story. They are the constraints that decide whether a story can survive. Curvature is one such constraint. If space has positive curvature on cosmic scales, it is shaped somewhat like the surface of a sphere extended into 3 dimensions. If it has negative curvature, it has a saddle-like geometry. If it is flat, parallel lines remain parallel in the large-scale sense. Measurements of the cosmic microwave background indicate that the observable universe is very close to flat. Inflation naturally explains this by stretching curvature until it becomes nearly undetectable. Some other models can also produce flatness, but they must do the work explicitly. Flatness does not mean the universe is small or simple. A flat universe can be infinite. It can also be finite in more complicated topologies. The part we see may be only a small region of a much larger shape. Cosmologists search for signs of topology, such as repeating patterns in the microwave background, but none has been confirmed. The universe may extend beyond our horizon in a way that never repeats within reach. This is another limit. The observable universe may not be large enough to reveal the whole geometry. The horizon problem, the flatness problem, the origin of fluctuations, the low entropy of the early universe, and the singularity problem are related, but not identical. A theory can solve one and leave another open. Inflation addresses several, but not necessarily all. A bounce may avoid a singularity, but must explain fluctuations and entropy. A no-boundary state may remove the first edge, but must connect to observed perturbations. This is why there is no simple scoreboard where one idea wins by sounding more satisfying. The details matter. The word singularity also appears in black holes, and that comparison can help. A black hole forms when matter collapses so strongly that an event horizon appears. General relativity predicts a singularity inside, but no observer outside the black hole can see the singularity directly. We infer the black hole through gravity, accretion disks, stellar orbits, gravitational waves, and shadows. Many physicists expect quantum gravity to change the deepest interior. The early universe singularity may be similar in one respect. It marks where classical theory points to its own incompleteness. There is an important difference. A black hole singularity, if it exists, lies inside a region of space-time. The Big Bang singularity, in classical cosmology, lies in the past of all regions of the universe. It is not a location one could avoid by traveling elsewhere. Every galaxy, every cluster, every void, every future planet, every atom in every star traces backward toward that same hot, dense origin. The beginning is not far away in a direction. It is beneath every direction in time. This is why cosmic origin questions feel intimate despite their scale. The atoms in your body were made long after the Big Bang, inside stars and stellar explosions, but the protons and neutrons in those atoms depend on conditions in the early universe. The hydrogen in water began as primordial hydrogen. The helium in stars is partly primordial helium. The cosmic microwave background passes through the space around you every moment. The question before the Big Bang is not about a remote object. It is about the earliest condition of everything that later became objects. If there was a previous universe, did any information survive into ours? This is one of the hardest questions. Information can be scrambled, diluted, or hidden behind horizons. A bounce could carry some features through, or it could act like a furnace that erases them. A previous contraction might imprint a different spectrum of fluctuations. Collisions with other bubble universes, if such things occur, might leave circular patterns in the microwave sky. Researchers have searched for such signatures. None has become accepted as proof. The absence of proof does not prove absence, but it narrows the room. Searches for unusual circles, cold spots, hemispherical asymmetries, and other large-scale anomalies in the CMB have produced debate for years. Some features are real in the map, but their significance is uncertain. A random field can contain strange-looking regions. Foregrounds and data processing can complicate interpretation. The more patterns researchers look for after seeing the data, the easier it becomes to find something that looks unlikely. This is called a look elsewhere effect. Serious cosmology has to account for it, even when the possible signal is tempting. The same caution applies to early galaxies observed by infrared telescopes. Some distant galaxies appear surprisingly mature or massive for their era, and these discoveries can challenge details of galaxy formation models. But they do not automatically overthrow the Big Bang. They occur hundreds of millions of years after the beginning, not before it. They may reveal that stars formed efficiently, that black holes grew quickly, or that early galaxy masses were overestimated at first. They are important, but they are not evidence of a previous universe by themselves. The earliest galaxies are still part of the story because they show how fast the universe turned from plasma to structure. After recombination came the cosmic dark ages, when neutral hydrogen filled space and no stars had yet ignited. Then, gravity pulled matter into the first halos. Gas cooled. The first stars formed, probably massive, hot, and short-lived. Their ultraviolet light began reionizing hydrogen. Their death seeded space with heavier elements. Black holes formed and accreted. The first galaxies became visible islands in a universe that had recently been dark. That transition does not tell us what was before the Big Bang, but it tests the chain of events after it. If the early fluctuation spectrum were different, galaxy formation would change. If dark matter behaved differently, small structures might form later or earlier. If expansion had a different history, distances and redshifts would shift. Observing cosmic dawn helps tighten the model, and a tighter model leaves less freedom for origin scenarios. Every new galaxy at high redshift is a small pressure applied to the theories of the first moments. Cosmology often advances by pressure rather than revelation. A measurement improves. An uncertainty shrinks. A class of models becomes less likely. Another class survives. The map grows sharper, but the earliest edge does not suddenly open. The universe is approached through limits: the opacity before recombination, the energy limit of accelerators, the cosmic horizon, the foregrounds that blur microwave polarization, the incompleteness of quantum gravity. These limits are not failures. They are part of the shape of the problem. A deeper problem is that there may be no external clock. In everyday cause and effect, one event causes another because it occurs earlier in time. If time itself begins with the universe, then asking what caused the beginning may require a different framework. Cause may not be fundamental there. It may be emergent, meaningful only after time has a direction and physical states can be ordered. This does not mean the universe appeared without explanation. It means explanation may not resemble a familiar chain of events. Physics has already forced this kind of adjustment before. Space and time were once treated as separate and absolute. Relativity joined them into space-time, where simultaneity depends on motion and gravity curves the paths of objects and light. Quantum mechanics changed the meaning of measurement, probability, and particle behavior. The early universe may require another adjustment, one in which time is not the background stage, but part of the system being described. That is a difficult idea because every sentence we use seems to assume time is already there. In some approaches to quantum gravity, space-time may be emergent from more basic relationships. The smooth fabric described by general relativity could be like fluid behavior emerging from molecules. Water waves do not reveal individual molecules directly, but they depend on them. In the same way, geometry might emerge from quantum information, networks, strings, loops, or other underlying structures. If that is true, the beginning of the universe may not be the beginning of everything. It may be the beginning of smooth spacetime as a useful description. Emergent spacetime ideas are difficult to test, but cosmology offers possible clues. Tiny deviations from standard predictions, relic gravitational waves, primordial non-Gaussianity, spatial curvature, or unusual correlations might point toward deeper physics. So might black holes, where quantum theory and gravity also meet. The information paradox, Hawking radiation, holography, and the thermodynamics of horizons all connect to questions about spacetime itself. The beginning and the black hole interior may be different doors into the same locked room. The holographic principle is one example of how strange the door may be. It suggests that the information content of a region of space can be related to its boundary area rather than its volume, an idea inspired by black hole thermodynamics. Some versions of quantum gravity use holography to describe spacetimes in terms of lower dimensional theories. This does not mean the universe is a projection in the casual sense. It means the bookkeeping of gravity and information may be very different from ordinary intuition. Whether this directly explains the Big Bang remains open. It is important not to turn every advanced idea into a claim. String cosmology, loop quantum cosmology, holographic cosmology, causal set theory, and other frameworks are active areas of research, not completed answers for a general audience to memorize. They provide possible languages. The universe may speak one of them, or none in their current form. A responsible script should not pretend that one has already won because it sounds elegant. The mystery is real because the evidence has not yet forced a final choice. Even without a final answer, the known history is astonishing. From a hot, dense state came a universe that cooled enough for nuclei, then atoms, then clouds of hydrogen, then the first stars. Galaxies formed along dark matter scaffolds, supernovae and neutron star mergers enriched space. Planets formed from disks of dust and gas around young stars. Some worlds became frozen moons, gas giants, rocky planets, asteroid belts, and comet reservoirs. On one planet, chemistry became biology, and biology built radio telescopes capable of detecting the afterglow of the beginning. That does not solve the before question, but it changes how the question feels. We are not asking from outside the universe. We are asking as matter inside it, using instruments built from its elements, interpreting radiation that has crossed its entire visible history. The question is not separate from the thing asking it. Every detector, every mirror, every cooled sensor, every superconducting circuit in a microwave telescope is a late product of the same cosmic process it tries to understand. The measurement of expansion also continues. Type 1a supernovae revealed in the late 20th century that cosmic expansion is accelerating. Baryon acoustic oscillations, galaxy clustering, gravitational lensing, and the cosmic microwave background all help refine the expansion history. There are tensions, including disagreement between some measurements of the Hubble constant made from the early universe and from the local distance ladder. Whether these tensions point to new physics or unresolved systematics remains uncertain. They remind us that even the later universe still contains unanswered questions. The Hubble tension does not automatically mean the Big Bang is wrong. It may reveal something subtle about dark energy, neutrinos, early dark energy, calibration, cosmic distances, or unrecognized measurement effects. Cosmology is precise enough now that small disagreements matter. But the broad evidence for a hot expanding universe remains strong. The question before the Big Bang must be asked within that strength, not as a replacement for it. Good mystery does not require pretending that established evidence is weak. Science is sometimes most honest when it says where its confidence ends. We can describe the universe from fractions of a second onward, with increasing confidence as time advances. We can describe nucleosynthesis, recombination, structure growth, star formation, and cosmic acceleration. We can infer earlier stages with models. We can test some aspects of inflation. We can propose bounces, quantum beginnings, cyclic histories, and no boundary states. But the absolute origin, if that phrase even applies, remains unresolved. There are different kinds of unresolved. Some questions are unresolved because the data have not yet been collected. Some are unresolved because the theory is incomplete. Some may be unresolved because the question is malformed. Before the Big Bang may contain all three possibilities. Better microwave polarization data could test inflation. Better quantum gravity could clarify the singularity. Better philosophical and mathematical language could reveal that before is not always a valid word. The mystery is not a blank wall. It is a junction of several incomplete roads. Future observations may narrow the roads. More sensitive CMB experiments could search for B-mode polarization and spectral distortions. Large galaxy surveys can map structure across enormous volumes. Gravitational wave observatories may someday detect backgrounds from early universe processes, though separating sources will be difficult. 21-centimeter cosmology could map neutral hydrogen from the dark ages and cosmic dawn. Each method reaches a different distance into the past. None promises a simple picture of before, but each can remove possibilities and sharpen the question. Spectral distortions are a subtle clue. The cosmic microwave background is extremely close to a perfect blackbody spectrum. Energy release in the early universe could have distorted that spectrum slightly. Measuring such distortions would reveal processes that occurred before recombination and after the earliest stages, potentially probing physics not visible in the standard temperature map. The difficulty is precision. The signal would be tiny. Foregrounds would be large. Instruments must compare the sky with extraordinary stability. Cosmology often depends on measuring almost nothing with great care. Gravitational waves offer another path because they can travel through plasma that light cannot cross freely. The gravitational waves detected so far by observatories on Earth have come from black hole and neutron star mergers, events in the relatively recent universe. A primordial gravitational wave background would be different. It would be a low murmur from the early universe itself, possibly from inflation, phase transitions, cosmic strings, or other high-energy processes. Detecting it would open a new window, not made of light, into times now hidden behind opacity. But gravitational waves also require caution. Different processes can produce backgrounds. Astrophysical sources, such as many unresolved black hole binaries, can create foregrounds. Instrumental noise can imitate patterns. Even a detection would require interpretation. A signal consistent with inflation might still fit more than one inflationary model. A signal inconsistent with simple inflation might support alternatives or point to new ingredients. The universe rarely labels its evidence. Humans must translate, and translation can be difficult. Somewhere in a data archive, there may already be a weak clue whose meaning is not yet known. A residual in a polarization map. A slight mismatch in a galaxy survey. A statistical feature that becomes significant only when the next instrument reduces the noise. Many discoveries look ordinary before they become discoveries. The microwave background itself was once unwanted noise. A black hole merger was once a tiny distortion in an interferometer arm. A planet around another star was once a repeated shift in spectral lines. Still, the most likely path is not one clue alone. It will be convergence. A theory of the earliest universe will become compelling when it explains several independent observations at once. It will match the CMB power spectrum, polarization, galaxy distribution, element abundances, curvature limits, and perhaps gravitational wave data. It will connect to particle physics or quantum gravity without arbitrary additions. It will make predictions that could have failed but did not. That is how a mystery becomes science rather than a story. The reference point for this is the Big Bang model itself. It survived because it explained expansion, predicted background radiation, accounted for light elements, and fit the growth of structure. It was not accepted because it was emotionally satisfying. In fact, many people resisted it for philosophical reasons. The model won by evidence. Whatever replaces or extends it will need the same kind of success. A pre-Big Bang theory cannot be accepted just because human minds prefer a cause before a beginning. There is also the possibility that different models describe different layers. Inflation could occur after a quantum beginning. A bounce could lead into inflation. A no-boundary proposal could set the conditions for an inflationary phase. A cyclic model could include periods of accelerated expansion. The options are not always mutually exclusive in simple ways. Cosmology may not end with one clean sentence. It may reveal a chain of phases, each requiring its own physics, each leaving only partial traces in the next. A chain like that would push the question further back again. What was before the quantum state? What set the law? Why these constants? Why this mathematical structure? At some point, physics may reach a boundary where asking for a prior cause is no longer useful, or where the answer becomes a deeper law rather than an earlier event. This is where cosmology touches philosophy, but it does not become philosophy alone. The physical evidence remains the anchor. Without it, the question drifts. Constants matter because small changes could alter cosmic history. The strength of gravity, the masses of particles, the amount of dark matter, the behavior of dark energy, the amplitude of primordial fluctuations, all influence whether stars, galaxies, and atoms can form. Some researchers use this to motivate anthropic reasoning in a multiverse. If many regions have different conditions, observers arise only where conditions permit complexity. Others dislike this because it can weaken prediction. The debate is not simply emotional. It is about what counts as explanation in a science with one observable universe. Anthropic reasoning may be useful in limited contexts, but it cannot replace measurement. Saying we observe a life-permitting universe because otherwise we would not be here is true, but incomplete. It does not explain the mechanism that produced the range of possibilities, nor does it always produce sharp predictions. If a multiverse is part of inflation or quantum cosmology, scientists still need to know how probabilities are defined, what values are expected, and whether any observable traces exist. Without that, the idea remains difficult to test. The observable universe itself is already enough to humble probability. It contains vast numbers of stars, but its early conditions were precise in ways still not fully explained. The microwave background is smooth to one part in about 100,000, yet not smoother than that. The density of matter allowed structure without immediate collapse. Expansion was fast enough to avoid recollapse, slow enough for galaxies to form. Dark energy became dominant only after billions of years. These facts are measured, not assumed. Their deeper explanation remains one of the reasons before the Big Bang matters. On the scale of human life, the early universe is almost unreachable. A century of astronomy has taken us from nebulae mistaken for nearby clouds to a measured cosmic history stretching back almost 14 billion years. That progress is astonishingly recent. The first galaxies outside the Milky Way were confirmed only in the last century. The cosmic microwave background was discovered within living memory for some. Gravitational waves were directly detected only in the 21st century. The tools are young. The question is old only because human curiosity makes it feel old. Instruments changed the question. Without radio astronomy, the microwave background would have remained hidden. Without space telescopes, infrared light from the earliest galaxies would be blocked or blurred by Earth's atmosphere. Without precise detectors cooled near absolute zero, tiny microwave variations could not be mapped. Without supercomputers, the growth of structure from initial fluctuations could not be compared in detail with surveys. The beginning of the universe is not approached by thought alone. It is approached by engineering, calibration, signal processing, and patience. A CMB detector must be shielded from the warmth of Earth, the Sun, and its own electronics. It must understand its own noise. It must scan the sky repeatedly. Data analysts must remove foregrounds, compare frequency bands, and estimate uncertainties. The final map looks clean, but cleanliness is earned. A galaxy survey must measure redshifts for millions of objects, correct for selection effects, and understand how dust and instrument limits bias the sample. Every elegant cosmological parameter rests on practical work. This practical work gives the mystery its weight. It is easy to say that science cannot solve what came before the Big Bang. It is harder and more accurate to say that science has pushed the question to a frontier defined by real data. The frontier moved from myth to philosophy, from philosophy to equations, from equations to telescopes, and from telescopes to precision maps of ancient radiation. It may move again. The fact that the answer is not known does not mean the question is beyond science forever. Consider the early plasma as a kind of cosmic instrument. Sound waves moved through it, driven by gravity pulling matter into denser regions and radiation pressure pushing back. Those waves froze into the microwave background when atoms formed. The peaks in the power spectrum are the notes left behind. By reading them, scientists infer the contents and geometry of the universe. This is not metaphor in the loose sense. The physics of acoustic oscillations is calculable. The early universe rang, and the pattern remains. If pre-Big Bang physics altered the initial conditions for those oscillations, it could leave a mark. Some bounce models predict a cutoff or suppression of power on large scales. Some inflationary models predict specific tensor modes. Some alternatives predict different non-Gaussian correlations. The data so far strongly support a simple, nearly scale-invariant spectrum with small deviations. That does not prove one origin, but it rules out many. The universe has already said no to countless mathematical possibilities by not displaying the patterns they require. The danger in origin stories is overconfidence. A beautiful model can feel true before it is tested. A strange anomaly can feel like a doorway before it survives statistics. A popular headline can turn a tentative paper into a supposed revolution. Cosmology attracts this because the subject is enormous and the evidence is subtle. But the early universe does not become clearer when uncertainty is exaggerated. It becomes clearer when uncertainty is placed exactly where it belongs. So what can be said now? The observable universe was once in a hot, dense, rapidly expanding state. It cooled. Light elements formed. Atoms formed. The cosmic microwave background was released. Structure grew from tiny fluctuations. Galaxies, stars, planets, and black holes emerged. There may have been inflation before the hot plasma phase fully developed. There may have been something before inflation. The classical singularity indicates that general relativity alone is incomplete at the earliest limit. A final theory of the beginning is not yet in hand. That answer is not small. It means science has reconstructed almost the entire visible history of the universe from traces arriving at Earth. The missing piece is not the whole story, but it is the deepest piece. It is the part where time, gravity, quantum fields, and the origin of order meet. The mystery remains not because scientists lack evidence for cosmic history, but because the evidence points toward a boundary where the next theory must be stronger than the ones we already have. The word before may survive. It may turn out that there was a previous contracting phase, a pre-inflationary state, or a larger multiverse background with a history of its own. In that case, before the Big Bang would mean earlier than the hot expanding phase that led to our observable universe. It would not be an empty darkness waiting for matter. It would be a physical condition governed by laws we are still trying to understand. The word before may also fail. It may turn out that time, as a meaningful classical dimension, begins with the universe, or emerges only after a quantum gravitational transition. In that case, the question would need to be rewritten. Not what happened earlier, but what condition gives rise to time. Not what caused the first moment from a previous moment, but why there is a temporal order at all. That answer would be stranger, but not less scientific if it made predictions and matched evidence. A third possibility is that the final answer is layered. Classical time may begin at the Big Bang, while a deeper quantum description exists without time in the ordinary sense. From inside the universe, we experience a sequence. From the deeper description, sequence may be approximate. This sounds abstract, but physics has often revealed that human scale categories are approximations. Temperature emerges from particle motion. Sound emerges from pressure waves. Space-time itself may emerge from something more fundamental. If that is true, then before the Big Bang might be like asking what a wave was doing before there was water in the description. The deeper system may not use the same terms. But analogies are dangerous. They can guide intuition and then mislead it. The actual answer, if it comes, will come from equations and observations, not from images alone. It may be less dramatic than expected and more difficult to state in ordinary words. The universe has already forced ordinary words to bend. A day means rotation, but before planets there were no days. A year means orbit, but before stars there were no years. A place means position relative to other things, but in the early universe there were no galaxies to mark locations. A cause means an event earlier in time, but at the edge of time that word may not hold. Each familiar term carries assumptions from a late, cold, structured universe. The beginning asks whether those assumptions survive. This is why the safest scientific answer is not a single object or event before the Big Bang. It is a map of possibilities constrained by evidence. Inflation is strongly motivated, but incomplete in mechanism. Bounce models are possible, but not confirmed. Cyclic models are intriguing but face entropy and observational challenges. No boundary and quantum cosmology proposals are mathematically serious but unsettled. Eternal inflation and multiverse ideas may arise from certain models but remain hard to test. The singularity is likely a sign of incomplete theory rather than a known physical point. In a shorter video, that might feel like no answer. In a long journey, it is the answer that exists now. Science has not failed to solve the mystery because it has nothing to say. It has revealed why the mystery is difficult. It has shown exactly where the light stops, where the equations strain, where the data remains silent, and where new physics must enter. That is progress of a quieter kind. Return to the microwave map on the screen. It is not a photograph in the usual sense. No galaxy is visible there. No star shines from it. It is a temperature field, a pattern of tiny variations in ancient radiation. Yet inside that pattern is the beginning of every visible structure that followed. The future Milky Way is not drawn there as a spiral, but its possibility is present in the density field. The future Earth is not there, but the conditions for stars and elements are beginning to assemble. A galaxy cluster bending light into arcs, a black hole casting a shadow in radio data, a nebula glowing in hydrogen emission, a planet crossing its star as a small dip in brightness, a gravitational wave stretching an interferometer arm, all belong to the later universe. They feel separate, but they are chapters of the same expansion. The question before the Big Bang is the question of what opened the book, or whether opening is even the right word. The observable record is chronological. First, the unknown quantum gravitational boundary. Then, perhaps inflation. Then reheating. Then the hot particle soup. Then, nucleosynthesis. Then plasma. Then recombination and the microwave background. Then, dark ages. Then, first stars and galaxies. Then reionization. Then the long growth of structure. Then heavy elements, planets, life, instruments, and the question asked by minds made from late cosmic matter. The unknown sits at the front, but the pages after it are not blank. Because the later pages are so detailed, any new first page must fit them. This is the discipline that keeps cosmology grounded. A theory cannot simply declare a previous universe because the idea is attractive. It must explain why the microwave background looks the way it does. It must not ruin nucleosynthesis. It must produce the right amplitude of fluctuations. It must allow galaxies to form. It must agree with limits on curvature and gravitational waves. It must survive comparison with the sky. There is humility in that. Not the humility of giving up, but the humility of not filling silence with certainty. The first instant is hidden. The conditions before inflation, if inflation occurred, are not known. The nature of time at the boundary is unresolved. The correct theory of quantum gravity is unfinished. A narrator can make this sound like a secret kept by the universe, but the better description is simpler. The measurements have not yet reached far enough, and the mathematics is not yet complete. Future scientists may look back on this era the way we look back on the time before the microwave background was discovered. They may find the missing signal and wonder how the answer remained unclear for so long. Or they may discover that several old questions were framed incorrectly. They may learn that the Big Bang was a transition, or that time emerged from a timeless quantum state, or that our observable universe is one region inside a much larger process. The answer may be stranger than any single current model. It may also be more modest. Perhaps no observable trace of a previous phase survived. Perhaps inflation erased the evidence. Perhaps the horizon keeps it forever beyond reach. Science can sometimes show that a question has no accessible empirical answer, at least for observers like us. That would not be emotionally satisfying, but it would still be knowledge. Knowing the limit is different from not knowing anything. Limits are part of astronomy. We cannot touch a star, yet we know its composition from spectral lines. We cannot see dark matter, yet we map its gravity through lensing and motion. We cannot visit distant galaxies, yet redshift and light curves reveal their history. We cannot photograph the first instant, but the microwave background and large-scale structure tell us how close our models come. The universe is studied through indirect evidence because almost everything important is out of reach. That indirect evidence has carried human understanding across distances no body can travel. The light from distant galaxies began before Earth existed. The microwave background began before atoms had assembled into stars. Gravitational waves from merging black holes cross space-time after events that released more power than all the stars in the observable universe for a brief moment. The instruments that receive these signals sit on a small planet, under weather, inside budgets, built by hands that live for decades. The scale mismatch is almost impossible to hold in the mind. Yet the signals arrive. A photon enters a mirror. A microwave detector warms by an almost immeasurable amount. A laser interference pattern shifts. A spectrum tilts toward red. A computer stores a number. From these events, the early universe becomes less hidden. Not fully visible, but less hidden. The question before the Big Bang remains, but it is surrounded now by a ring of evidence, each point marking something that must be true after whatever came before. The phrase "science still cannot solve" should not be read as "science never will." It means the current evidence and theory do not yet force a final answer. The history of astronomy is full of questions that once seemed unreachable. What are the stars made of? How far away are the spiral nebulae? Do planets orbit other suns? Do black holes exist physically? Does the universe have a beginning? Each became answerable through new methods. The before question may require methods not yet mature, or instruments not yet built, or mathematics not yet found. It may also require accepting that the beginning is not an event inside time. That is harder than building a larger telescope. A larger telescope can gather more light. A new theory must change the frame in which light, time, and space are understood. The hardest part may be conceptual, not technological. The universe may have no need to arrange its origin in a way that fits the human grammar of before and after. Even so, the question keeps its power because it is precise enough to guide research and open enough to remain alive. It asks about inflation, quantum gravity, entropy, time, causality, and the limits of observation. It touches the microwave sky and the mathematics of singularities. It connects the smallest scales to the largest structures. It is not merely a question of curiosity. It is a question about whether the laws we know are complete. The laws we know are already remarkable. General relativity predicts the bending of light by gravity, the expansion of the universe, black holes, gravitational waves, and time dilation. Quantum field theory underlies particle physics and the behavior of matter and radiation. Thermodynamics explains the arrow that runs through stars and life. But a full origin theory may need all of them at once. it may need a way to describe quantum fields in a dynamical spacetime at energies far beyond experiments, under conditions where the entire observable universe was compressed into an unimaginably hot state. If the early universe passed through a phase transition, like water freezing or boiling, but at an energy scale far beyond ordinary matter, that transition could have produced relics. Cosmic strings, gravitational waves, or other defects might remain as signatures. No confirmed cosmic strings have been found. But the search illustrates the method. The early universe may have changed states as it cooled, and each change may have left faint marks. The more marks we can measure, the closer we come to the boundary. Phase transitions are already part of early universe physics. The electroweak force and electromagnetic force separated. Quarks became confined into protons and neutrons. Matter and antimatter somehow ended with a slight imbalance, leaving the matter that later formed galaxies. These events occurred after the absolute earliest unknown, but they show how cosmic history can depend on particle physics. The origin of the matter-antimatter asymmetry, called baryogenesis, is still not fully solved. It is another clue that the early universe contains missing physics. Baryogenesis matters because a universe with equal matter and antimatter would have annihilated almost completely into radiation. The fact that matter remains means that early processes treated matter and antimatter slightly differently under conditions not yet fully understood. This does not answer what came before the Big Bang, but it belongs to the same frontier. The first moments shaped not only space and time, but the existence of the material from which stars, planets, and bodies would later form. A tiny imbalance in the early universe became everything solid we know: hydrogen clouds, galaxy disks, iron cores of planets, ocean water, telescope mirrors, human bones, meteorites, dust grains in nebulae, the carbon in living cells. All of it depends on matter not vanishing into radiation. When origin questions are treated as abstract, this is easy to forget. The earliest physics is not remote from the later universe. It is written into every piece of matter that survived. There is another old question near the beginning. Why is there something rather than nothing? Physics can address parts of it, especially when nothing is defined as a physical vacuum or quantum state. But the broadest version may not be fully scientific unless it can be made into a testable form. Cosmology does not erase that question. It refines it. Instead of one enormous sentence, it breaks the mystery into measurable pieces: expansion, temperature, density, fluctuations, curvature, entropy, fields, and time. That refinement is not a loss of wonder. It is the way wonder becomes durable. A vague mystery can dissolve into any answer. A measured mystery resists easy answers. The cosmic microwave background resists invention because it has a spectrum and a temperature. Galaxy surveys resist invention because they have positions and redshifts. Element abundances resist invention because they can be compared with nuclear physics. The beginning remains open, but not open to everything. Some claims about before the Big Bang will always travel faster than the evidence. Headlines may announce that scientists have found what existed before everything, or that a new telescope has disproved the Big Bang, or that a simulation has revealed another universe. Most of the time, the real paper is more careful. It proposes a model, investigates a possibility, resolves a tension under certain assumptions, or offers a new way to test old ideas. The gap between headline and evidence is wide, and the early universe lives in that gap too often. A careful viewer should ask simple questions. What does the model predict? Has the prediction been observed? Is the signal unique? Or could other processes produce it? What assumptions are required? Does it match the microwave background, nucleosynthesis, structure formation, and expansion history? Has it been independently checked? These questions do not remove the mystery. They protect it from being replaced by noise. Noise itself is part of the story. Radio noise revealed the microwave background. Detector noise challenges gravitational wave searches. Photon noise limits deep images. Cosmic variance limits how well we can know the largest scales because there is only one observable universe. Noise is not just an obstacle, it defines the sensitivity of knowledge. Sometimes the signal is buried in it. Sometimes the signal looks like it until the instrument improves. Cosmic variance is especially important for the largest patterns in the microwave sky. On small angular scales, there are many independent regions to measure. On the largest scales, there are only a few modes across the sky. This limits how precisely we can determine whether a large-scale feature is unusual. Even a perfect instrument would face this limit. The universe gives us one cosmic microwave background sphere around us, not many independent universes to compare. This is why some questions may remain probabilistic. We may never know whether a particular large cold region in the CMB is a statistical accident or a sign of deeper physics, unless other evidence supports it. A single anomaly rarely carries the weight of a new universe. Multiple converging anomalies, predicted in advance by a theory, would be different. Cosmology depends not only on detecting patterns, but on understanding how often patterns appear by chance. The early universe was simple in composition compared with today, yet difficult in physics. Today, the universe is full of structures: spiral galaxies, elliptical galaxies, dwarf galaxies, clusters, black holes, stars, planets, comets, and dust. The beginning had none of these, but its energies were extreme, and its laws may have operated in ways not directly accessible now. Simplicity of appearance did not mean simplicity of explanation. A smooth plasma can hide deeper questions than a sky filled with galaxies. A processed image from a telescope often uses color to make invisible wavelengths visible. Infrared becomes red or gold. X-rays become blue or violet. Radio data become brightness on a screen. Cosmology does something similar with time. It translates redshift into distance and look-back time. It translates microwave fluctuations into density variations. It translates equations into histories. We never see the beginning directly. We see translations, and good science remembers that translation is involved. Translation can be checked. The same cosmological parameters inferred from the microwave background can be compared with supernovae, galaxy clustering, lensing, and primordial element abundances. Agreement increases confidence. Disagreement exposes either new physics or hidden error. This web of cross-checks is why the hot Big Bang model is robust. It is not one image or one number. It is a structure supported from several sides. The mystery before the Big Bang lies beneath that structure, not in place of it. Removing the hot early universe would break too much evidence. Extending it is the task. Perhaps the correct theory will say that the Big Bang was a boundary of classical spacetime, not of existence. Perhaps it will say that a previous phase collapsed and rebounded. Perhaps it will say that our region emerged from an inflating background. Perhaps it will say that time has no earlier edge because the concept of earlier fails. Each answer changes the meaning of the title. The title asks what was before the Big Bang. A careful response begins by defining Big Bang. If it means the hot, dense, expanding phase, then there may have been inflation before it, and perhaps something before inflation. If it means the absolute beginning of classical spacetime, then before may not be meaningful. If it means the singularity in classical equations, then the answer is that known physics breaks down and quantum gravity is required. Different definitions produce different answers. Much confusion comes from mixing them. In public imagination, the Big Bang often becomes a single instant. In technical cosmology, it can refer to a model of expansion and cooling, not necessarily the first moment. The earliest confirmed stages are not the same as the earliest imaginable stages. A scientist may speak of the hot Big Bang beginning after inflation, while another may use Big Bang for the entire early expansion. When asking what came before, the vocabulary must be slowed down. Otherwise, people argue across different meanings. There was no sound in the ordinary sense at the Big Bang, because sound needs a medium and pressure waves, and the early plasma did have acoustic oscillations, but not sound heard by ears. There was no flash seen from outside, because there was no outside observer and no transparent space for light to cross until later. There was no center, because expansion occurred everywhere. These corrections can feel less cinematic, but they make the real event more interesting. The Big Bang was not an explosion in space. It was the early expansion of space with matter and radiation in it. The real event is harder to picture than an explosion. Every point in the observable universe was once part of that hot, dense state. The space between your eyes, the space between Earth and the Moon, the space between galaxies, all trace backward to a smaller scale factor. Not to a point located somewhere else, but to an earlier condition of all locations. The center is not missing. The concept of a center is the wrong tool. A wrong image can lead to wrong questions. If the Big Bang is imagined as an explosion into emptiness, then before seems like the empty space waiting for the explosion. But if space itself is part of the expansion, then there may be no pre-existing emptiness. The question becomes about the origin, or prior state of space-time itself. That is a more difficult question, but it is also closer to the physics. Think again of the microwave background. It surrounds us because it comes from every direction, but it is not a shell centered on Earth in a special way. Every observer in the universe would see their own background sphere, coming from the matter that became transparent at the right distance and time for them. The CMB is a surface of last scattering, not a wall at the edge of creation. It is a time surface seen at a distance. This idea helps explain why looking far away is looking into the past. A galaxy 1 billion light-years away is seen as it was roughly 1 billion years ago, with corrections for expansion. A galaxy at very high redshift is seen much earlier. The microwave background is seen from a time when the universe was 380,000 years old. But there is no light-based image from before that, because the universe was opaque. To go earlier, scientists need indirect signals, polarization, gravitational waves, abundance patterns, or theoretical reconstruction. The earliest possible direct messenger may not be light, but gravity. Gravitational waves interact weakly with matter, so a primordial background could carry information from times when photons were trapped. Neutrinos also decoupled early and form a cosmic neutrino background, but detecting it directly is extraordinarily difficult with current technology. These hidden backgrounds are like older pages sealed beneath the visible page. They may exist all around us, but existence is not the same as accessibility. Accessibility defines the frontier. The cosmic neutrino background should be present as a relic from the early universe, much older than the microwave background, but its particles are so low in energy and so weakly interacting that direct detection remains beyond present experiments. If detected, it would confirm another part of early cosmic history. It still would not necessarily answer what came before the Big Bang, but it would move observation closer to the hidden era. The beginning is therefore not one locked door, but a corridor of locked doors. Recombination was once a door, opened by microwave astronomy. Nucleosynthesis is opened through nuclear physics and element observations. Inflation is partly approached through fluctuation statistics and polarization. Quantum gravity remains further in. Pre-Big Bang possibilities lie beyond that, unless they left traces that passed through every later door. The challenge is to know which traces could survive. Some traces cannot survive in recognizable form. A star from a previous cycle would not pass through a Big Bang like hot, dense state intact. Molecules, atoms, nuclei, and perhaps even particles as we know them, would be destroyed or transformed. Any memory would have to be encoded in fields, geometry, correlations, or conserved quantities, not in objects. There would be no ancient planet older than the Big Bang drifting in our universe as a relic from before. That kind of story belongs to fiction, not cosmology. Even black holes from a previous universe are not straightforward. Some speculative models discuss primordial black holes or objects passing through bounces, but there is no confirmed evidence that black holes older than our hot Big Bang exist. Primordial black holes could have formed in the early universe from density fluctuations after the Big Bang, not necessarily before it. They are interesting as dark matter candidates or probes of early conditions, but they should not be treated as proven relics from a previous cosmos. If anything from before survived, it would likely be subtle. A tilt in a spectrum. A missing range of fluctuations. A background of gravitational waves. A non-random correlation across the sky. A value of curvature too large for certain inflationary models. A pattern in the distribution of galaxies. The oldest evidence may not look old. It may look like a small number in a table, with uncertainty bars and a long caption. That is not disappointing. It is how the universe often reveals itself. Neptune was found through a deviation in Uranus's orbit. Exoplanets were found through tiny stellar wobbles and dips in light. Dark matter appears through motion and lensing. Black holes appear through orbits, accretion, mergers, and shadows. The most important things are not always seen directly. They are inferred because their effects are too consistent to ignore. A pre-Big Bang theory will need effects too consistent to ignore. It may not show a previous universe as an image. It may show that a certain pattern cannot be produced by inflation alone, or that a bounce model predicts a feature later observed in several independent datasets. It may connect with a quantum gravity theory that also explains black hole entropy or particle physics. The answer may arrive not as one discovery, but as a network of discoveries that begin to point the same way. Until then, the honest answer remains conditional. Before the hot Big Bang, there may have been inflation. Before inflation, there may have been an earlier physical state, or a quantum origin, or no classical before at all. The singularity in simple models is not a confirmed object, it is a breakdown. The universe may have begun, bounced, emerged, or transitioned. Science has not yet solved which of those words is correct. The uncertainty is not weakness, it is the shape of a frontier. A finished answer would be easier to narrate, but less truthful. The early universe is one of the rare subjects where human knowledge can be extraordinarily precise and profoundly incomplete at the same time. We can quote temperatures, ages, redshifts, and abundances, and still not know whether the first moment was a beginning or a bridge. Precision and incompleteness coexist in the Planck mission results. The satellite measured the cosmic microwave background in exquisite detail and helped refine parameters such as the age of the universe, the density of ordinary matter, the density of dark matter, and the shape of the primordial fluctuation spectrum. Those numbers make cosmology a precision science. Yet the same data do not identify the inflaton, prove a multiverse, confirm a bounce, or describe quantum gravity. The map is detailed, but the earliest caption is missing. The missing caption may be written in mathematics not yet discovered. It may involve a symmetry, a quantum state, a deeper geometry, or a relation between information and space-time. It may be connected to why constants have their values, or why the vacuum energy is so small compared with naive expectations. The cosmological constant problem, the nature of dark energy, and the origin of inflation may be linked, or they may be separate puzzles that only seem connected because they are all difficult. It is possible to overconnect mysteries. Dark matter, dark energy, inflation, quantum gravity, and the Big Bang are not interchangeable unknowns. Each has its own evidence and constraints. Dark matter acts gravitationally in galaxies and clusters. Dark energy describes accelerated expansion. Inflation is a proposed early rapid expansion. Quantum gravity seeks to unite gravity with quantum principles. The Big Bang model describes hot expansion and cooling. They may connect in a deeper theory, but a responsible explanation keeps them distinct until evidence joins them. The universe is connected enough without forcing it. The same expansion that cooled the microwave background also stretches light from distant galaxies. The same gravity that shaped tiny early fluctuations now holds galaxy clusters together. The same nuclear physics that made helium in the first minutes powers stars billions of years later through fusion. The same space-time curvature that governs cosmic expansion bends light around massive clusters into arcs. The whole history is one physical system unfolding over time. At the beginning of that unfolding, we meet a blur. Not because the rest is vague, but because the beginning is where our maps overlap poorly. General relativity points backward. Quantum theory waits at small scales. Thermodynamics asks why the early state was special. Observations provide traces but not direct sight. The blur is not empty. It is crowded with unfinished physics. A useful way to think about the current answer is to divide it into layers of confidence. Highest confidence, the universe has expanded and cooled from a hot, dense state, leaving the microwave background and light element abundances. Strong but still model-dependent, an early period like inflation may explain the observed smoothness, flatness, and fluctuations. Speculative but serious, there may have been a bounce, no boundary origin, eternal inflation, cyclic history, or emergent spacetime phase. Unknown, which, if any, describes reality before the hot Big Bang. The layers matter because they keep the narrative from flattening. Not all ideas have equal support. The cosmic microwave background is observed. Primordial gravitational waves from inflation are not yet confirmed. The abundance of helium and deuterium supports nucleosynthesis. A previous contracting universe is not confirmed. Expansion is observed. A multiverse is not observed. This distinction is not a detail. It is the difference between science and speculation. Speculation still has a place when it is disciplined. It creates models, and models can lead to tests. Without speculative imagination, there would be no inflationary theory, no black hole thermodynamics, no gravitational waves predicted a century before detection. But speculation must remain aware of its status. Theories at the edge of the Big Bang are invitations to look, not declarations that the looking is finished. There may never be a human sense of standing at the beginning. No final image may appear. No telescope may show a glowing point labeled first cause. The answer, if it comes, may be a set of equations whose consequences match several subtle observations. It may feel less like opening a door and more like realizing that several measurements had been describing the same hidden room all along. That would still be one of the greatest discoveries in science. To know whether time began, whether the universe bounced, whether inflation was preceded by something deeper, whether space-time emerged from quantum information, would change the meaning of cosmic history. It would not make galaxies less real or stars less luminous. It would place them inside a deeper structure. The Milky Way would still turn. The cosmic web would still stretch across billions of light years. Black holes would still merge and ring spacetime. Nebulae would still collapse into stars. Planets would still form from dust around young suns. But the background against which all of it happened would be different. The first page would no longer be blank. It would have shape. For now, the shape is inferred only at the edges. The CMB map waits on screens and in archives. Its small variations are measured again and again. New telescopes look past foreground dust. New surveys chart galaxies in 3 dimensions. Theories are written, tested, revised, and sometimes abandoned. The question remains open, but it is not untouched. Every careful measurement presses against it. The mystery science still cannot solve is not whether the universe has a history. It does. It is not whether the Big Bang model has evidence. It does. The mystery is whether that history has an earlier chapter, and if it does, what kind of chapter could exist before time, space, matter, and radiation behaved as we know them. The answer may be a previous universe. It may be inflation without a known start. It may be a quantum boundary. It may be the end of the word before. In each case, the deepest challenge is the same. We are trying to describe a condition where the tools of description may have been forming. We use clocks to ask about time, rulers to ask about space, causes to ask about beginnings, and equations built inside the universe to ask about the origin of the universe. This is not impossible, but it is delicate. The mathematics must be strong enough to carry words where intuition cannot. The reason science has not solved it yet is therefore clear. The observations reach back far, but not all the way. The theories work well, but not together at the necessary limit. The candidate ideas are serious, but not decisive. The word before is meaningful in some models and questionable in others. The data constrain the possibilities without choosing one. That is the current state of the mystery. If a future detector finds primordial B-mode polarization, the story will change. If a future gravitational wave observatory detects a background with a spectrum pointing to a phase transition or cosmic strings, the story will change. If quantum gravity produces a clear prediction and the sky matches it, the story will change. If galaxy surveys and CMB data continue to favor simple inflation while ruling out alternatives, the story will narrow. The answer is not frozen. It is waiting on both instruments and ideas. Waiting does not mean passive. Observatories are being designed. Data are being analyzed. Theoretical models are being compared against constraints. Cosmologists argue over assumptions, priors, measures, foregrounds, and interpretation. This is not noise outside the science. It is the science. A question this old cannot be solved by a single dramatic sentence. It has to be handled until weak ideas break and stronger ones remain. Perhaps that is the most important difference between mystery and myth. A myth can preserve a question by protecting it from testing. Science preserves a question by exposing it to testing again and again. What was before the Big Bang remains alive because it has not been answered, but also because it has not been abandoned. It sits inside equations, observing proposals, detector designs, and arguments about the first meaning of time. One way to understand the frontier is to follow the clock backward as far as current physics allows, not as a countdown to a known zero, but as a sequence of regimes. At about 380,000 years, atoms form and the microwave background escapes. At minutes, light nuclei form. At fractions of a second, particles interact in a dense radiation bath. At still earlier times, forces that appear separate today may have been unified or connected in ways that only high-energy physics can describe. The clock becomes less like a calendar and more like a warning label. Beyond this range, the model is useful. Beyond that range, the model is provisional. The electroweak era is one such provisional region. At energies far above those in ordinary stars, the electromagnetic force and the weak nuclear force behave as parts of a unified electroweak interaction. As the universe cooled, this symmetry broke, and the forces took on the separate forms observed today. This kind of transition is not simply a detail from particle physics. In the early universe, a change in the behavior of a field could affect expansion, matter production, and possible relic signals. A small shift in high-energy physics can echo across cosmic history. The strong nuclear force has its own transition. Quarks and gluons, free in an extremely hot state, became confined into protons, neutrons, and other particles as the universe cooled. This quark-hadron transition occurred long before atoms and stars, but after the deepest unknown. It shows that the young universe changed character more than once. It was not one continuous fog from beginning to galaxies. It was a sequence of changing physical conditions, each one opening and closing different possibilities for matter. Some proposed relics from early transitions have never been seen. Magnetic monopolies are a famous example. Certain grand unified theories predict particles with a single magnetic pole, but none has been confirmed. Inflation was partly attractive because it could dilute such unwanted relics to unobservable levels. That is useful if the relics would otherwise be overproduced. But it also shows how early universe theories can interact. Particle physics creates a problem. Cosmological expansion offers a possible solution, and observation decides how much room remains. A universe before the Big Bang would have to pass through this sequence, or explain why the sequence began. If there was a bounce, the rebound had to lead into conditions hot enough for known early processes. If there was a no-boundary state, it had to produce a universe with the right fields and symmetries. If there was eternal inflation, one pocket had to reheat into the particle content we observe. The later universe is not optional. It is the test every earlier idea must meet. Reheating is one of the least visible but most important parts of the story. In many inflationary models, the energy driving inflation does not remain as smooth vacuum like energy forever. It decays or transfers into particles, filling the universe with radiation and matter. This reheating stage links the inflationary universe to the hot Big Bang. Without it, inflation would leave space empty and cold. With it, the universe becomes a dense thermal bath from which the familiar early chronology can proceed. The details of reheating are uncertain because they depend on the inflaton field and its couplings to other particles. How fast did energy transfer? What particles were produced? Was the process smooth or violent? Could it have generated gravitational waves, primordial black holes, or matter-antimatter asymmetry? These are not decorative questions. They determine whether inflation is only a geometric smoothing event or also the furnace that set the contents of the universe. The before question may hide inside this transfer of energy. A poorly understood reheating stage also reminds us that the Big Bang is sometimes used for several different moments. The public word points to the beginning. The technical phrase hot Big Bang often points to the hot radiation-filled state after inflation, if inflation happened. Reheating would be the bridge between them. In that sense, what came before the Big Bang might mean what came before reheating. The answer could be inflation, but then the deeper question remains: what came before inflation? And why was inflation possible? The deeper question cannot be solved by making inflation longer. If inflation goes on far enough into the past, it faces mathematical and conceptual problems. If it begins at a finite time, it needs an initial condition. If it is eternal into the future, producing many regions like ours, that does not automatically make it eternal into the past. Cosmologists debate these issues because they determine whether inflation is an origin or only a stage after an origin. Origins are difficult because they ask physics to explain not only motion, but the condition from which motion begins. A planet's orbit can be predicted if its position and velocity are known. A star's evolution can be modeled if its mass and composition are known. The universe has no surrounding system from which initial data can be handed in. Its initial condition is part of the problem. The whole system must somehow include the rule and the starting state. In ordinary science, initial conditions often come from a larger environment. A molecular cloud collapses because turbulence, gravity, magnetic fields, and nearby stars shape it. A crater forms because an asteroid arrives from an orbit determined by earlier gravitational encounters. A supernova occurs because a star formed with a certain mass. The universe as a whole may not have that kind of external environment unless a larger cosmological framework exists. If no such framework exists, the origin must be explained in another way. This is one reason quantum cosmology treats the universe itself as a quantum system. Instead of asking for a previous classical state, it asks what wave function, boundary condition, or path integral could describe a universe. These are technical ideas, and they do not produce simple pictures. They also face the problem of time, because standard quantum mechanics usually assumes an external time parameter. In quantum gravity, that external time may not exist. The theory must explain time from within. A timeless equation is not the same as a timeless experience. We experience sequence, memory, aging, and change. A cosmological theory without fundamental time would still have to explain why time appears so reliably inside the universe. It would need to show how classical spacetime emerges, how clocks become meaningful, and why entropy gives one direction to the history we observe. Without that bridge, a timeless origin remains a mathematical idea without a full connection to the world of measurements. Some physicists compare this to a frozen landscape that contains paths within it. The whole structure may be described without an outside clock, while observers inside perceive movement along one direction. But again, analogies can only carry the thought a short distance. The real issue is whether the formalism produces the universe we see. A timeless equation that cannot produce the microwave background, expansion history, and arrow of time is not enough. The arrow of time may be the hidden key. If the universe began in a very special low entropy state, then the question becomes why that state existed. If the low entropy came from a previous phase, then that previous phase must be explained. If it came from a boundary condition, then the boundary condition must be justified. If it came from a quantum state, then that state must be selected by some principle. Each answer pushes the mystery into a different language. A previous contracting universe might seem to explain the arrow by making the bounce a transition from earlier to later. But contraction usually makes gravitational clumping worse, not better. Structures grow. Black holes form. Entropy increases. To produce a smooth expanding universe after a bounce, a model must prevent the contracting phase from becoming chaotic or singular in the wrong way. Ekpyrotic models attempt this through slow contraction with a very stiff equation of state, smoothing space before the bounce. Whether nature used such a process remains unknown. The phrase equation of state may sound remote, but it simply describes how pressure and density relate for the dominant cosmic component. Radiation behaves one way. Matter behaves another. Dark energy behaves differently. In the early universe, unusual fields could have unusual equations of state, and those behaviors could change whether contraction smooths or destabilizes the cosmos. This is the kind of detail that separates a serious model from a vague idea of a universe bouncing back. A bounce must also handle perturbations, the tiny variations that later become galaxies. It is not enough for the average universe to bounce. The fluctuations must pass through the bounce with the right spectrum and amplitude. They must not grow uncontrollably. They must not produce a microwave background unlike the one observed. This is technically difficult. It is also what makes the models scientific. They have to do more than avoid a singularity. They have to seed the actual sky. Conformal cyclic cosmology offers a different kind of prehistory. In that proposal, the remote future of one cosmic aeon is mathematically related to the Big Bang of the next. The far future, after black holes evaporate and massive particles lose relevance, can be rescaled so that it resembles a new beginning. It is an ambitious idea, associated with deep questions about time, mass, and geometry. It has inspired searches for circular patterns in the microwave background, but it has not become established cosmology. Claims of observed circles or special features in the CMB must be treated cautiously. Other researchers have disputed their significance, and the standard model remains broadly successful. This does not make the cyclic proposal worthless. It means the evidence has not forced acceptance. A model can be mathematically interesting and still unconfirmed. The distinction matters especially for a topic where audiences are tempted to treat every alternative as a discovery. Another unusual idea is a CPT symmetric universe, where the universe before the Big Bang is related to ours by charge, parity, and time reversal symmetry. In broad terms, such a model can imagine a mirror cosmic history on the other side of the beginning. It is not a picture of another galaxy beyond a wall. It is a symmetry-based proposal about the structure of physical law across the Big Bang boundary. Like other ideas, it seeks testable consequences, such as implications for neutrinos or dark matter candidates. The fact that these models exist shows that the before question has not been ignored. It has been attacked from many directions: inflationary field theory, quantum gravity, string-inspired brain models, loop cosmology, conformal geometry, symmetry principles, and thermodynamics. The variety can be confusing, but it reflects the size of the gap. When the data do not yet decide, several mathematical roads can remain open at once. A road begins to close when it predicts something the universe does not show. If a model predicts strong curvature and observations find near flatness, it struggles. If it predicts large non-Gaussianity and the CMB does not contain it, it loses ground. If it overproduces relic particles, fails nucleosynthesis, or prevents galaxies from forming, it cannot describe our universe. In this way, even absence is useful. The sky has ruled out more universes than it has confirmed. But ruling out is slower than announcing. It takes data, careful statistics, and independent checks. An early universe model may survive by adjusting parameters, or by adding fields, or by changing assumptions. At some point, too much flexibility becomes a weakness. A theory that can fit anything predicts little. Cosmologists value models that are constrained enough to risk failure. The best answer to before the Big Bang must be vulnerable to the universe. This vulnerability is one reason researchers care about simple parameters such as the scalar spectral index. The primordial fluctuations are not exactly the same strength on every scale. Their slight tilt carries information about early physics. Planck and other data measure this tilt with increasing precision. Many inflationary models predict values close to what is observed. Some alternatives can also fit it. Future measurements may refine the distinction, especially when combined with tensors, non-Gaussianity, and other signatures. The tensor-to-scalar ratio is another crucial number. It compares primordial gravitational wave fluctuations to density fluctuations. A high value would support certain large-field inflation models and reveal the energy scale of inflation. A very low value would rule out those models but not inflation as a whole. Current observations place upper limits, and the search continues. In a script about before the Big Bang, this number matters because it is one of the few possible handles on physics far earlier than the microwave background. The running of the spectral index, the detailed shape of the power spectrum, the distribution of polarization, the lensing of the CMB by later structure, and the statistics of galaxy clustering all add smaller handles. None by itself may solve the origin. Together, they make the early universe less free to be anything. A model of before must pass through all of these narrow gates. There is a quiet irony in this. The farther back we ask, the more we depend on precision in the present. The cleanest statements about the first fractions of a second come from instruments sitting near Earth, measuring faint photons, correcting for dust, and comparing maps. The beginning is approached by reducing error bars. The largest question in time is answered, if it is answered, through the smallest differences in data. Laboratory physics also matters. Particle detectors do not reproduce the Big Bang, but they test the ingredients. The Higgs field, neutrino masses, matter-antimatter violation, dark matter searches, and high-energy collisions all constrain what the early universe could have done. If a proposed cosmology requires particles or interactions that experiments exclude, it weakens. If a new particle is discovered, early universe models may change. The cosmos and the laboratory are not separate sciences here. The Higgs field is especially interesting because it is a scalar field known to exist, while inflation is usually modeled with a scalar field not yet identified. Some models explore whether the Higgs itself or a related field could drive inflation, but this requires specific couplings and assumptions. It is tempting to connect known physics to cosmic origins because it reduces invention. But the connection must work quantitatively. A familiar name does not automatically solve the beginning. Neutrinos also carry early universe importance. They are light, abundant, and weakly interacting. Their masses affect structure formation. Their number and behavior influence the radiation density in the early universe. Cosmological data constrain the sum of neutrino masses and the effective number of relativistic species. If future measurements find deviations, they could point toward new particles or interactions in the early universe. Again, before the Big Bang may be approached through subtle measurements of what survived after it. Dark matter could also be tied to the earliest moments. If dark matter is a particle, its abundance may have been set by freeze-out, freeze-in, axion dynamics, primordial black hole formation, or another process in the young universe. Each mechanism belongs to a different thermal and expansion history. Finding dark matter would not automatically reveal what came before the Big Bang, but it would remove one major unknown from the cosmic model and sharpen the conditions near the beginning. Dark energy, by contrast, shapes the late universe but may echo vacuum energy questions that also appear in inflation. The observed acceleration of expansion is extremely small compared with naive estimates from quantum fields. Why vacuum energy has the value it does is one of the deepest puzzles in theoretical physics. Inflation also involves vacuum-like energy, but at a much higher scale. Whether these are connected is unknown. The similarity in language should not be mistaken for a proven link. The beginning and the end may still speak to each other. In the far future, if dark energy continues behaving like a cosmological constant, galaxies beyond our local group will disappear beyond the horizon. The cosmic microwave background will redshift to wavelengths too long and cold for future observers to detect easily. Evidence of the Big Bang may become inaccessible. We live in an era when the sky still holds the clues. That gives present cosmology a strange urgency. A civilization in the far future, isolated in one merged galaxy, might not easily discover cosmic expansion. It might see no distant galaxy redshifts, no accessible microwave background, no obvious large-scale structure. The evidence we now use could fade from practical reach. This does not answer the before question, but it reminds us that knowledge depends on cosmic timing. The universe is not equally legible at every age. We happen to exist after the microwave background cooled into detectable wavelengths, after galaxies formed, after heavy elements made planets, and before cosmic acceleration hides too much of the large-scale universe. This timing may be necessary for observers like us, but it is still remarkable. The question before the Big Bang is being asked during an epoch when the evidence after the Big Bang is unusually rich. This richness includes meteorites and planetary materials, even though they formed billions of years after the beginning. A meteorite in a laboratory can reveal isotopes made in ancient stars. Those stars trace back to early galaxies, which trace back to primordial fluctuations. A slice of rock from the solar system does not speak directly about inflation, but it belongs to the chain of evidence showing how matter evolved from early hydrogen and helium into complex chemistry. Cosmic history is continuous even when the origin is hidden. The cosmic distance ladder does similar work in the other direction. Cepheid variables calibrate supernova distances. Supernovae measure expansion. Expansion links to the cosmic model. The cosmic model links to early conditions. Each rung has uncertainties, and those uncertainties matter. When local expansion measurements disagree with early universe inferences, cosmologists have to examine every rung. The origin question is influenced by the reliability of measurements made in comparatively nearby galaxies. The same is true of gravitational lensing. Massive clusters bend light from background galaxies into arcs and distorted shapes. Weak lensing across wide fields maps the distribution of matter, including dark matter. This helps measure how structure grows over time. Growth depends on the initial fluctuation spectrum and the expansion history. A map of faint galaxy shapes billions of years after the Big Bang becomes another test of what the early universe was allowed to be. Nothing in cosmology stands alone. A cold microwave photon, a helium atom in a distant gas cloud, a red galaxy in an infrared image, a lensing arc around a cluster, a supernova light curve, a gravitational wave chirp, and a simulation of dark matter filaments all touch the same underlying history. The before question sits beyond them. but they form the bridge as far as the bridge currently reaches. When a simulation begins, it often starts with a box of dark matter and initial fluctuations drawn from a spectrum measured in the microwave background. The computer evolves particles under gravity, allowing halos and filaments to form. Gas physics, star formation, black hole feedback, and radiation can be added in more complex simulations. Researchers then compare simulated galaxies and clusters with observations. If the simulated universe resembles the real one, it supports the initial conditions. If not, something may be missing. Simulations are not evidence by themselves. They are controlled experiments inside assumptions. They can show what a model implies, but they cannot prove the assumptions are true. Their value comes from comparison. A simulation of a bouncing universe, an inflationary universe, or a modified dark matter model must meet the sky. Beautiful images of filaments are not enough. The numbers must match. This is another reason the opening map matters. The cosmic microwave background is not only a relic, it is an input for understanding everything after it. It anchors simulations, constrains parameters, and provides a surface against which early theories are judged. The map is like the oldest page of an archive, but also like the first frame of a calculation that produces galaxies. Behind it is darkness to light. In front of it is the entire visible history of structure. If we could somehow see before recombination with ordinary light, the view would not be a landscape. There would be no stars approaching, no clouds, no horizon in the familiar sense. The universe would be a glowing plasma, opaque in every direction. Go earlier, and even nuclei dissolve. Earlier still, the distinction between familiar particles changes. The first moments are not hidden behind distance alone. They are hidden behind changes in the state of matter and the limits of interaction. A detector does not complain about this. It simply records what reaches it. Human beings do the complaining, because our imaginations want a scene. Cosmology often denies scenes. It gives spectra, distributions, and correlation functions instead. The discipline of the subject is learning to treat those as real. A power spectrum is not less physical than a photograph. It is a different way the universe leaves a trace. A photograph can deceive by feeling immediate. A power spectrum can feel abstract while being more informative. The temperature map of the CMB tells the eye something. The spectrum of its fluctuations tells physics much more. It reveals the relative heights of peaks, the damping at small scales, the imprint of baryons and dark matter, and the geometry of space. The deeper universe is often most visible when the image is turned into mathematics. This transformation from image to mathematics also protects against overinterpretation. A spot on a map can look meaningful. A statistical analysis asks how likely it is under a model, how sensitive it is to masking, how foregrounds affect it, and whether other data confirm it. The first reaction may be wonder. The second must be measurement. That rhythm is the voice of cosmology at the edge of the Big Bang. It is possible that the decisive clue will not come from the CMB at all. It could come from a particle discovered in a detector, a dark matter signal, a measurement of neutrino properties, a gravitational wave background, or a mathematical breakthrough in quantum gravity that makes a clear cosmological prediction. The before question has many entrances because the early universe involved all of physics at once. A final theory may therefore look less like astronomy alone and more like a merger of disciplines. General relativity, quantum field theory, thermodynamics, particle physics, information theory, and observation will have to meet. The Big Bang is not merely an astronomical event, it is a boundary problem for physics. It asks whether the laws known from laboratories and telescopes are parts of one deeper law that can describe the whole universe. Even if that deeper law is found, the word why may remain layered. Physics can explain how one state follows from another, or why certain conditions are probable under a theory, or why a symmetry requires a result. But why there is a law at all may be a different kind of question. Cosmology can push explanation deeper, but it may not convert every form of why into a measurement. Recognizing that boundary is part of being honest about the mystery. The strongest answers science gives are not always the most emotionally complete ones. The universe may be described by a principle that feels impersonal. It may have no human-like reason. The desire for a cause may be a feature of minds that evolved inside time, where causes are survival tools. At the beginning, cause may be replaced by boundary condition, quantum amplitude, or consistency requirement. That can feel cold, but coldness is not evidence against it. At the same time, science should not retreat too quickly into saying the question is meaningless. Sometimes questions that seem confused become meaningful after theory improves. Before relativity, asking how time changes with motion sounded strange. Before quantum mechanics, asking about probability at the heart of matter sounded incomplete. Before modern cosmology, asking about the age of the universe seemed speculative. The before question may be waiting for a better language rather than deserving dismissal. A better language would need to connect to instruments. Otherwise, it remains private mathematics. The power of physics is that its most abstract ideas eventually risk contact with the world. General relativity risked contact with Mercury's orbit, starlight bending, gravitational redshift, black holes, and gravitational waves. Quantum theory risked contact with spectra, semiconductors, lasers, and particle collisions. A theory of the beginning must find its risks too. Those risks may be small numbers, a tensor to scalar ratio below a threshold, a particular non-Gaussian shape, a curvature sign, a relic background, a particle property, a spectral distortion. The answer to what came before the Big Bang may first appear as a constraint in a paper, not as an image on a screen. Years later, the meaning may become clear. Many scientific revolutions begin as technical details. There is patience built into this. The universe took hundreds of thousands of years to become transparent, hundreds of millions of years to form the first galaxies, billions of years to form Earth, and billions more to produce beings capable of asking about its origin. The instruments now built are only the first generations of cosmic archaeology. They are good enough to ask the question sharply, not necessarily to finish it. Cosmic archaeology is an imperfect phrase, but useful. Archaeologists dig through layers left by past lives. Cosmologists dig through light, redshift, and radiation left by past states. In archaeology, a broken shard can change the understanding of a settlement. In cosmology, a small deviation in polarization could change the understanding of the beginning. Both sciences depend on fragments. Both require restraint in interpretation. The fragment we have from 380,000 years is enormous in extent but limited in depth. It covers the whole sky, yet it comes from one time. The fragment from nucleosynthesis is chemical, preserved in the abundance of light elements. The fragment from structure formation is gravitational, preserved in galaxies and clusters. The fragment from expansion is kinematic, preserved in redshift. Each fragment is different. Together they make a history. None alone is the first cause. If a previous universe existed, it may be almost completely absent from this history, like an earlier manuscript scraped from parchment and overwritten. Sometimes traces of the old writing remain under the new. Sometimes they do not. The cosmic microwave background may be the overwritten page where any surviving marks would have to be found. The difficulty is knowing whether a faint mark is ancient writing or damage from the scraping. That is why caution returns again and again. It is not a way of making the story dull. It is the only way the story stays connected to reality. The universe before the Big Bang, if there was one, will not become real to science because it is vivid. It will become real if its consequences are measured. Until then, the most accurate image is not a hidden world waiting behind a curtain, but a set of possible histories narrowed by a visible sky. Another part of the problem is that the universe does not provide a laboratory control group. There is no second cosmos beside ours where inflation lasted a different length of time. No neighboring sample where the constants were changed. No repeated beginning that can be measured under different conditions. Cosmologists use the sky as a statistical field, but the field belongs to one universe. That makes the discipline powerful and limited at once. It can measure patterns across enormous volumes, yet it cannot rerun the beginning to see what changes. This single sample problem affects the deepest claims. A model might say that our universe is typical within a larger ensemble, but if the ensemble is not directly observable, typical becomes difficult to define. Another model might say that the beginning was uniquely determined, but uniqueness is hard to prove when alternatives can be constructed. The question before the Big Bang therefore presses not only on physics, but on the method of cosmology itself. It asks how much can be known from one sky. One answer is that one sky can still contain many independent measurements. The small-scale fluctuations of the CMB, the distribution of galaxies at many redshifts, the abundance of elements, the lensing of light, and the expansion rate are not the same observation. They are different consequences of the same early conditions. Agreement among them is meaningful. It is not as strong as rerunning the universe, but it is far stronger than a single clue. The fact that these clues agree is why the hot Big Bang is not in serious doubt among cosmologists. Debate lives at the edges: the nature of inflation, the Hubble tension, dark matter identity, dark energy behavior, quantum gravity, and the earliest boundary. Those debates are not signs that the whole structure is collapsing. They are signs that the structure is precise enough for its unfinished parts to stand out. Sometimes precision creates new mysteries. A rough map can hide a discrepancy. A sharper map reveals it. When the early universe was studied with less accuracy, many models survived comfortably. As observations improved, some models failed. Others became strained. A few remained. The mystery before the Big Bang is therefore not getting vaguer with time. It is being compressed into a smaller and more difficult space. That compression can be seen in the way inflationary models are tested. Simple versions once allowed wide ranges of predictions. Measurements of the spectral tilt and limits on primordial gravitational waves have ruled out or disfavored some of them. This does not eliminate inflation, because other versions remain viable. But it changes the field. Theories adapt or disappear. The sky does not answer loudly, but it does answer. A similar narrowing may happen for bounce models. If future observations find a particular kind of primordial gravitational wave background, certain bounces might struggle. If a large-scale cutoff or non-Gaussian signal appears, some alternatives might gain ground. If no such signs appear and inflationary predictions keep succeeding, bounces may become less compelling. The question is open, but it is not frozen in place. Data move it. There is also the possibility of a surprise that does not fit any favored model. Astronomy has a history of finding objects and signals that were not the thing being searched for. Pulsars were not expected in the way they appeared. Quasars forced a new understanding of active galactic nuclei. Gamma-ray bursts puzzled astronomers for decades. The microwave background itself appeared as unwanted noise. The first clear clue to pre-Big Bang physics may arrive sideways, disguised as a problem in another field. If that happens, the first task will not be celebration. It will be elimination. Is the signal instrumental? Is it local? Is it produced by the Milky Way? Is it caused by known astrophysics? Does it appear in independent instruments? Does it persist under different analysis methods? Only after the ordinary explanations fail does the extraordinary interpretation become credible. The earlier the claimed origin, the heavier this burden becomes. The Milky Way is a foreground for cosmology. Its dust, gas, magnetic fields, synchrotron emission, and stars lie between us and the distant universe. To study the beginning, scientists must subtract parts of the galaxy we live inside. That is a strange situation. The home galaxy is both a subject of astronomy and an obstacle to seeing earlier cosmic history. A grain of dust in a local spiral arm can complicate a claim about the first fraction of a second. The solar system is a foreground too in some measurements. Zodiacal light from dust near the plane of the planets affects infrared observations. Earth's atmosphere affects ground-based telescopes. The ionosphere alters low-frequency radio waves. Human radio transmissions contaminate parts of the spectrum. Detectors age. Mirrors deform slightly. Calibration sources have uncertainties. The path to the beginning passes through all of these mundane details. This is why the most distant science often depends on the least glamorous labor. Cleaning data. Modeling dust. Testing detectors. Comparing pipelines. Understanding noise. Reobserving the same field. Publishing limits when no detection is found. These acts do not look like grand cosmic revelation, but they make revelation possible. Without them, the before question would be only imagination with equations attached. When the first stars formed, they began adding complexity to a universe that had been chemically simple. Their light rayonized hydrogen, their explosions made heavier elements, and their remnants may have become early black holes. This happened long after the Big Bang. Yet it matters because it marks the first time the universe produced many of the astrophysical foregrounds that later complicate our view backward. The cosmos made the lamps, then the lamps began to obscure the oldest glow behind them. A deep infrared image from a space telescope can show a field crowded with galaxies, each one a system of stars, gas, dust, dark matter, and often a central black hole. The oldest light in that image is still not old enough to be the beginning. It is the universe, after it learned to make stars. Behind those galaxies, in time, is neutral hydrogen. Behind that is the microwave background. Behind that is plasma. Behind that is particle physics. Behind that is the unresolved boundary. Following that sequence prevents the mind from jumping too quickly from galaxies to creation. The first galaxies are astonishing, but they are not first things. The CMB is ancient, but not the first event. Nucleosynthesis is early, but not the origin. Inflation, if real, is earlier, but may not be ultimate. The Planck scale is a frontier, but not an answer. The beginning is approached through stages, and each stage must be kept in its place. This is also why the phrase "seeing the Big Bang" is inaccurate. We do not see it. We see the afterglow from a later transparent epoch. We infer earlier conditions from that afterglow and from other evidence. The difference is not pedantic. If the public imagines that a telescope has photographed the Big Bang itself, then the hidden parts of the problem disappear. The real achievement is subtler and greater. Scientists inferred the unseen from what the universe allowed to travel. A similar correction applies to the size of the early universe. People often imagine all matter compressed into a tiny ball. But if the entire universe is infinite today, it may have been infinite then as well, only denser everywhere. The observable part was once compressed to a much smaller volume, but that is not necessarily the entire universe. The Big Bang model describes the scale factor and density, not an object with an outer surface. The observable universe can have a finite horizon even if the whole universe is infinite. This distinction is central. We can only receive signals from a finite region because light has traveled for a finite time through expanding space. Beyond that region may be more of the same cosmic web, or something more varied, or structures forever disconnected from us. We do not know. The before question sits beyond a temporal horizon, while the beyond question sits beyond a spatial one. Both remind us that observation has edges. The edge of observation does not necessarily mark the edge of reality. Ancient sailors seeing a horizon did not see the end of Earth. Astronomers seeing the cosmic horizon do not see the end of the universe. But unlike a ship, we cannot simply sail beyond the cosmic horizon and send back a map. Expansion and the speed of light make some regions permanently inaccessible. Cosmology must therefore be careful about claims that extend beyond what can ever affect us. If other bubble universes exist, they may be beyond such an edge. If a previous cycle existed, most of it may be beyond a thermal edge. If time emerged, the prior description may be beyond a conceptual edge. Each edge is different. The danger is treating them all as the same darkness. The discipline is to name the edge precisely: horizon, opacity, singularity, quantum gravity regime, or limits of language. Naming the edge precisely changes the mystery. The CMB is an opacity edge for photons. The Planck era is a theoretical edge for current physics. The cosmic horizon is an observational edge from expansion and finite light speed. The singularity is a mathematical edge in classical general relativity. A philosophical question about why laws exist is a different edge altogether. What was before the Big Bang crosses several of these, which is why simple answers tend to fail. A viewer may still ask what scientists personally believe. Some favor inflation with a beginning still unknown. Some explore eternal inflation. Some work on bounces. Some prefer no boundary or tunneling proposals. Some expect quantum gravity to remove the singularity without a classical before. Others are skeptical that the question can be answered observationally. The diversity of opinion is not random. It reflects different judgments about mathematics, evidence, simplicity, and what kinds of predictions are most valuable. Consensus exists only where evidence is strong enough. There is consensus that the universe expanded and cooled from a hot, dense state. There is strong support for the broad standard model with dark matter and dark energy, though its ingredients remain mysterious. There is no consensus on the ultimate beginning. That boundary between consensus and open research should remain visible. It is where the title lives. If the answer someday becomes consensus, it will probably feel obvious in retrospect. The microwave background now seems like a natural relic of a hot beginning, but before it was detected, cosmology was less settled. Continental drift once seemed radical before plate tectonics connected evidence from geology, magnetism, and seafloor spreading. Scientific answers often look inevitable only after the evidence has organized itself around them. For now, the evidence is organized around the hot Big Bang, not around a single pre-Big Bang extension. That is the honest stopping point. It leaves room for imagination, but not for certainty. It allows a narrator to enter the darkness before the first light, but only with instruments in hand: a microwave map, a spectrum, an abundance table, a gravitational wave limit, a simulation, and a theory that can fail. A final complication is that every origin model has to explain why mathematics applies so effectively to the universe at all. Equations written on Earth describe the cooling of plasma billions of years before Earth formed. They describe nuclear reactions in the first minutes and light bending around clusters billions of light years away. This effectiveness is not usually treated as part of cosmology, but near the beginning it becomes difficult to ignore. If the laws themselves are part of what emerged, then a deeper theory must explain not only the first state, but the reliability of law-like behavior from that state onward. Cosmologists usually proceed by assuming that the laws observed here apply throughout the observable universe and back into the early periods where they have been tested indirectly. This assumption is not blind faith. It is supported by spectra from distant galaxies, the uniformity of physical processes, and the success of models across time. Hydrogen absorbs and emits light in the same recognizable way across cosmic distance. Gravity shapes clusters in ways equations predict. The microwave background matches thermodynamics with extraordinary precision. The universe appears lawful across the region we can study. Whether those laws extend unchanged through the first boundary is less certain. Symmetries may have been restored at high energy and broken as the universe cooled. Constants may be fixed by deeper fields or by features of a larger theory. Dimensions beyond the familiar three of space and one of time may exist in some frameworks, compact or hidden from ordinary scales. These ideas are not part of everyday astronomy. but they appear near the origin because ordinary scales no longer protect familiar physics. Extra dimensions, if they exist, should not be imagined as simple hidden rooms next to space. In most theories, they are mathematical dimensions with specific geometry and physical consequences. They may influence particle properties, gravity, or early universe behavior. No confirmed evidence for them has appeared. Their role in pre-Big Bang scenarios remains speculative, but they show how far physicists have had to extend the language of geometry to search for a complete beginning. String-inspired cosmologies sometimes imagine brains, higher dimensional objects, whose motion or collision could produce a hot expanding universe. In such models, what we call the Big Bang may be related to a collision or transition in a higher dimensional setting. This is not an explosion in ordinary space, and it is not supported by direct observation. It is an attempt to use a possible deeper framework to replace the singular beginning with a physical event. The value of the idea depends on whether it can produce testable differences. Testable differences are the thread through every serious proposal. A brane collision might produce a different gravitational wave background. A loop quantum bounce might alter the largest scale CMB modes. A no-boundary condition might favor certain inflationary histories. A multiverse model might imply statistical expectations for curvature or vacuum energy. Though defining those expectations is difficult. The details are technical, but the principle is simple. A theory should leave the universe slightly different in a way instruments might eventually notice. If no difference can ever be noticed, the theory may still be mathematically interesting, but it becomes hard to call it an empirical answer. This is where cosmologists disagree. Some argue that a theory can gain support if it is the best part of a broader framework that explains many other things. Others insist that direct or indirect cosmological predictions are necessary. The debate is serious because the beginning may lie partly beyond direct access. Science must decide how far inference can responsibly reach. Reaching too far risks turning cosmology into storytelling. Reaching too little risks abandoning questions that may actually be answerable. The balance is difficult. The history of science contains both warnings, elegant ideas that failed, and bold ideas that waited decades for confirmation. Gravitational waves were once beyond detection. Exoplanets were once uncertain. The cosmic microwave background was once a prediction awaiting a receiver. The beginning may require the same patience, but patience is not the same as certainty. One practical way forward is to improve every part of the chain. Better foreground maps improve CMB studies, better measurements of galaxy clustering test structure growth, better supernova calibration informs expansion history, better particle physics constrains early interactions, better numerical simulations connect initial conditions to observed galaxies. Better mathematics clarifies whether singularities are physical or removable. No one improvement solves the mystery, but each one tightens the net. The net may one day catch a contradiction. If the standard model cannot fit future data without strained additions, a new early universe phase may become necessary. Or the net may catch confirmation, showing that a simple inflationary picture with a particular field fits everything new. Or it may catch a stranger result, evidence that the words beginning and before need replacement. The most honest position is to allow the evidence to surprise us. There is a quiet discipline in allowing surprise. It means not deciding in advance that the universe must have come from nothing, or must have bounced, or must be one bubble among many, or must have begun time itself. Each possibility carries a different emotional flavor, but emotion is not a measurement. The universe will not choose the answer that feels most complete to a human mind. It will choose the answer it already followed. For now, the first confirmed chapter remains the hot young universe, bright, dense, expanding, and nearly smooth. Behind it is a region where the evidence thins and the theories multiply. That region is not a failure of science, it is the current edge of it, where telescopes, detectors, equations, and careful uncertainty all arrive together and look for a way through. The most difficult mysteries are not always the ones with no evidence. Sometimes they are the ones with evidence leading almost, but not quite, to the answer. The Big Bang is that kind of mystery. The trail is bright for nearly the whole history of the universe, then becomes faint at the exact place where the question becomes deepest, where better instruments and better theories still have to meet, patiently, carefully, and without shortcuts from here onward. The safest final answer, then, is layered rather than absolute. We know the universe passed through a hot, dense early state. We have strong reasons to think an even earlier inflation-like phase may have occurred, though its engine is unknown. We know the classical equations point toward a singular boundary, but we also know those equations are incomplete at such extremes. We do not yet know whether that boundary hides a previous phase, marks the emergence of time, or signals a transition described by quantum gravity. The mystery remains because all three possibilities are still scientifically alive. At the end of the night, a radio dish turns beneath a sky that looks mostly dark to human eyes. The darkness is real, but it is not empty. Microwaves from the early universe pass through it. Starlight from distant galaxies crosses it. Neutrinos stream through it almost unnoticed. Gravitational waves stretch it by amounts too small to feel. The sky is full of messages that require the right instrument to become visible. The oldest visible message says the universe was hot, dense, smooth, and seeded with tiny differences. It does not say what came before. It carries the question to the edge and leaves it there. Behind it may be inflation. Behind inflation may be a quantum state, a bounce, a larger cosmic landscape, or no behind in the usual sense. The mystery is not a lack of story. It is a place where several possible stories meet the silence of current evidence. And so the first light remains on the screen, cold now, stretched across the sky, carrying a pattern older than every star. Scientists can measure it, filter it, map it, and compare it with theories. They can follow its traces forward into galaxies and backward toward physics that is not yet complete. But when the calculation reaches the earliest boundary, the map becomes unfinished. Not empty, not meaningless. Unfinished. Somewhere in that unfinished edge is the answer to what came before, or the reason before was never the right question. Until then, the universe gives us what it has always given us: light that has traveled too long to be young, signals almost lost in noise, equations that work until they do not, and a sky that keeps allowing the past to arrive one photon at a time.